Hello everyone and welcome to yet another recreation programming session with Mr. Zozin as usual. So here I have an ARM machine, right, and it's not really physical machine, it's an emulator, right? So we actually set it up on one of the previous stream. And so what I want to do today, I want to do a little bit of ARM development because I have a language that I'm developing in here. It's a compiler for B programming language, the original B programming language by Ken Thompson and Dennis Ritchie that was before C, right? And currently it supports only x86-64, right? It can also compile to JavaScript, but it's not particularly well supported target, right? So, and I set up this emulator specifically because I want to add another target, another compilation target to this language, which is ARM. So, and that's what we're going to be doing today, right? So, it shouldn't be that difficult. This language has its own backend, right? So, but it's actually a very simple backend. It's a few intermediate representation instructions, and the thing we need to do in here is just port these instructions to ARM, right? So we can take a look at that. So here is the compiler. Here's the compiler, and it's written in Crust, right? Well, it's written in Rust, but in a subset of Rust called Crust, which is basically an unsafe subset of Rust. So if you want to learn more about this kind of thing, you can actually check out this repo. Right, it explains the rules of Crust and the purpose of this subset of Rust. I'm gonna also put this thing in the description. So I'm telling you that upfront, so you don't get scared when you see a lot of like weird things, like all the functions are unsafe and we're using row pointers everywhere. That's kind of the whole point, right? So that's Crust. So essentially how all of that works, we are reading the file, right? So you have a source code, you're supplying that source code through command line arguments, we're reading that file, we tokenizing it, and we compiling that file, right? So there is a compiler that maintains the state of the compiler, and then we're generating the program out of the state of the compiler. So there's this function, right? And basically, depending on the target, right, so we're generating each individual function in here, right? Depending on the target that you supplied in there, we're generating the functions differently, right? So for example, we have FASM x86-64, and what we're doing, we're just like taking an array of ops which are intermediate representation instructions of the body of the function. We're literally iterating them, and then we're basically switch casing. In Rust it's called matching them, and on each operation, right, so we look what it is and we're generating corresponding assembly code. That's what we're doing, right? So there's quite a few of them. We don't support the entirety of the B compiler, and there's not that many intermediate representation instructions, which is good, right? So which should make it a little bit easier to actually port. So if we take a look at what kind of stuff we have in here, so here's struct op. Well, it's not really struct, it's enum op. So this is how many intermediate representation instructions we have right now. Not that many, right? So you have unary not. So you have binary operations, and the amount of binary operations that we have in here. So let's take a look at that. So binop, it's like 4 of them. Right, so basically, instead of this single intermediate representation instruction, consider these to be 4 instructions. Right, so this is actually 4 because inside of it we have like sort of a code that denotes what kind of operation is that. Right, so we have assignment, we have function calls, and we have conditional and unconditional jumps. Right, so this allows us to have a little bit of a mathematical operations. We can call to external functions, and we can also organize the loops through conditional and non-conditional jumps. The kind of programs that you can write in this language right now is, for example, I think one of the most complex program is this Fibonacci numbers. Right, so you can declare external symbols, which it will take from C runtime. Even though it's a B programming language, we link with the C runtime because it implements a lot of useful functions, so it lets us bootstrap the language a little bit quicker. So we allocate a bunch of variables on the stack, right? So we assign the first 2 Fibonacci numbers, we organize the loop, so we're generating numbers below 1 million, and every time we iterate, we print the number, and then we compute the next Fibonacci number. So the way it works, right, so we can just do something like this. So here is the compiler. You're just supposed to provide the input, right? So example fib, and it does the compilation, right? So it first generates an assembly file with x86-64 assembly. So here is basically the Fibonacci program, but generated into low-level assembly. Then what it does, it turns this assembly into object file, and then it calls the external linker to link that file with a C runtime, right? So I also implemented recently a pretty cool flag which is called dash run, and it automatically runs the program auto compilation. So you can just do things like that. So essentially, if I ever want to implement like a build system for in B, right, so I don't have to do this weird trick with go rebuild yourself in knob, right, because majority of the mainstream compilers don't allow you to just compile and run simultaneously. B automatically allows you to do that, right, so you can just build and run, which is quite convenient. So on top of that, recently for this compiler, I implemented, you know, adding additional flags to the linker, because it calls an external linker at the end. So if you want to customize how linker works, you can add additional flag, which enables you quite conveniently working with other libraries, third-party libraries, like for example Raylib. And in fact, we do have example with Raylib in here. So here it is. So I actually demonstrated how it works on the previous stream, right? So we actually implemented that on the previous stream, but I recently made it more complex, right? I added a rectangle that moves around and stuff like that. And you can compile it, you know, quite easily by using additional like linker flags. So let's give it a try. I'm gonna go here and might as well just do something like this, raylib.b, right? As you can see, it cannot find any of the raylib functions, right? So as far as I know, I actually put raylib library in opt in a home folder, so here it is. So now I can do the following thing. So give me home opt raylib lib, right? And since it's kind of a nested sort of like L means that I'm gonna append a linker flag. I lost it. Freaking I lost it. L means that I'm gonna append the linker flag, and within the linker flag I need to do a dash L again, right? So and then here I'll have to do opt raylib lib like so, but then I have to kind of concatenate it like that, right? So but then I have to also say, all right, link it with lib raylib.a. And it actually linked. Now it wants a math library. So let's actually add math library. And as you can see, it actually compiled and it actually linked, right? So after that, I can do, you cannot see shit, by the way. So let me bring the camera a little bit up so you can see now. I can actually quite easily add the ran flag and it will run this entire thing. But I mean, there's a little bit of a bug. You have to do something like this. Yeah, there we go. So, and the program works. Right, and you can continuously modify it and rerun it and so on and so forth. For example, if I don't like the red square, I can do something like that, run it again, and there we go, it's green. And it's not an interpreted language, by the way. It compiles to assembly, right? It legit compiles to assembly, then it, you know, translates it to object file and then links and stuff like that. So it's a proper language, more or less, right? Even though it's a subset of B programming language, it's still, you know, it works. So pretty cool. Let's fucking port that to ARM. How about that? How about that? I wonder if you can even build my compiler on ARM. Can I do that? So let's actually see. So do I have Git? I don't have Git. So let's actually install it. So here we have Alpine, right? So that means I can basically list this kind of stuff. Is this how it works? I think this is how it works. So what do we have in here? So yeah, so here's the Git. So apk add Git. Let's fucking go. We're installing Git. Installing Git. We got Git. How about that? So let me actually now clone the B compiler. Right, so we have a bunch of things in here. So here are the projects. Might as well maybe create like a separate folder in here called programming. Right, so and move hello into programming. Right, and move hello awesome into programming as well. So we have a separate folder where we do all the programming, and I'm gonna git clone the whole thing into here. Hopefully it will work. Okay, so we have a B compiler. So that's pretty cool. So it's inside of the virtual machine. So do we have Rust? So I'm pretty sure like you're supposed to use Rust up to set up Rust, but maybe the Rust exists in APK. Usually the distros like don't maintain their Rust like very frequently. So I actually doubt that it's gonna be there. No, there is Rust, and so this is the latest version. Is that the latest version? I'm actually curious. So if I do something like a Rust C version, yeah, and I'm not even sure if that's the latest one. So Rust up upgrade, right? So that's how we upgrade. So let's actually wait a little bit. It usually takes some time, so maybe in the meantime, Oh, actually, okay. So I thought maybe we can talk with the chat, but I mean, it's the latest one. And this one is not the latest one. So should I just install this one or try Rust up? So Rust lang. So we can try Rust up. So get started, get farted. So it's kind of funny that the language that is all about security and safety just offers you to download a random shell script from the internet and pipe it into Sage. But you can trust us because we're the good guys, am I right? Right, so just like we're the good guys. So obviously we can do that. It's the bad guys that can't do that. The good guys can do that. Curl doesn't even exist. Okay, so apk add curl. Let's install curl. All right, so can I just do that? I wonder if it's going to work. Will it automatically detect that it's Arch? Okay, so this is interesting. We'll add in your path, blah, blah, blah. You can install, proceed with the standard installation. Okay, so let's actually proceed with the standard installation. All right. So, and by the way, this may take some time. So let's actually put the chat in here. So how's it going, everyone? How's it going? Does it matter whether it's a shell script or executable? Well, a shell script is kind of human readable sometimes. So, I don't know. It's kind of difficult to tell. The shell script itself can always contain actual executable, maybe in some sort of strings or something, then output it into the file system and execute it anyway. So you can basically store executables inside of shell scripts, right? So it's just like it doesn't really matter. Don't get full chat, neither the S in HTTPS nor in TLS stands for safe, true. Can you have graphical programs in ARM? Probably, but I'm not sure about this setup. This setup doesn't have access, right? So we can install access, but then we have to output it somewhere. We can try to do that, right? So, because as far as I know, we just need to set up the device for the QEMU, right? It's all running inside of a QEMU, right? And I'm SSHing into the QEMU machine. So I have one question. In a stream where you were writing a wrapper for MPV and used flags.h, there was a comment on the code regarding memory leak. Can you please help me understand how did you identify that leak in a child process? I guess you used execvp. The leak is caused by appending to CMD. Right, so let me see, where is the, it's actually gatekeeper. CMD, MPV client, so leak. You see, memory leak is caused by CMD append because CMD append allocates memory. Each append in here allocates memory, and it's all done in the current process, right? It's actually not in the child process, right? So yeah, that's a good point. It's actually not in the child process, but it's just in the current process. And then we substitute the image of the process with a new image. And that program, the image of which we used, doesn't know anything about these allocations. So it by definition cannot deallocate any of the memory in here. But it's fine because it's a one-time allocation and not repeated allocation in a loop. In that sense, it's not really a memory leak. Don't even worry about it. Don't think about it. It's fine. It's totally fine. So okay, so it's done. Look at that. Look at that chat. Look at that chat. We got Rust. What the fuck is new? New. Is that a new shell? Is that what this thing uses? Like APK new shell? I never heard about it. I thought it's bash. New shell, a new type of shell. Huh. Never heard about it. So what's so special about it? Oh, it's written in Rust, I see. Okay, so that means there's nothing special about it. It's just like written in Rust for the sake of being written in Rust. Okay. It's not even used, bro. Freaking Mozilla. Who's developing Rust? Rust Foundation, but it's like used to be part of Mozilla. What the fuck are you using your Google money for? Like, you can't even automatically detect the shell I'm using and just give me the proper... Holy shit. Jesus fucking Christ, Brovsky. I thought, like, I looked at the last thing and I thought that maybe it automatically detected my shell and just for my shell specifically, it suggested this kind of thing. Then I didn't look at any of these things in here. It just dumped all of the possible versions in here. And, okay, the question is, why only 3 then? Why only 3? Why stop at 3? Like, just provide for everything. Why select it? This is so bizarre. Right, it's just like... For fuck's sake. Anyways, so we have Rust. Right, so it's a Rust C. Okay. Anyways, so probably to just promote their shell. Okay. So where is the B? B. Clang. We need Clang. Okay. So grab Clang. Jesus fucking Christ, Brovskis. So which one do I have to install? So can I just install Clang and do everything automatically for me? Or do I have to install a specific version? Which version do I have in here, by the way? I'm curious. So I have 18. Look at that. 18. So let's install 18 then. So add Clang 18. Let's fucking go. I wonder for how long it's gonna go. So it's only 8 packages. Right, so hopefully it's not gonna go for too long. Hopefully it's not gonna go too long. Alright, so can we rebuild that stuff? Okay, Clang, no such, really? Is that because it's a Clang? Damn. Okay, so can I just install Clang? Okay, I can apparently, but that's gonna be Clang 19. It's a little bit bizarre, honestly. Alright, so in that case, can I just delete Clang 18 then? Because I don't really need it, right? So since I'm going to be using 19 anyway. Right, so here's the version. And yeah, it's 19. So I can go, and it's building things. Damn, it's going to take some time to build all of that stuff. It doesn't build very fast. Oof. That is weird. Why? So, did they change in the latest... Right, so what Rust version is this? What Rust version is this? It's the same as mine, isn't it? Is that the same commit? It is even the same commit, but it doesn't behave the same way as in here. So they're saying that my string literals are U8. Did they change R? Oh my god. Rust up doc. C char. So here's the C char. OS row. Let's take a look at the source code of this thing. So I didn't see type. So it probably has to be maybe through FFI. Let's take a look at the FFI because that's the one that we're using here. So this is a C char definition. I have a hypothesis. That maybe on ARM it's actually different. So what is a C char definition? C char definition, okay. So section the ARM C and procedure. Right, so let's take a look. All right, data types, unsigned byte. Okay. So, and now, where is x86-64? I didn't see. This is a target on which CHR is a... Okay. So this is a target and sign. Usually the signers is the same for all target OS values on given architecture, but there are some exceptions. C is sign character default in Clang. Damn, I just learned something. I didn't even know it's a thing. So, but why? See arithmetic types of fundamental type in table 3. Do they even explain why? So is signed Clang. So GitHub. Is there a Clang? So here is LLVM project. And this is the entirety of LLVM project, right? So let's actually try to clone it. Do I even have enough like space for all of that stuff? So home 5 gigabytes. God fucking damn it. I probably won't have enough for the LLVM because LLVM is pretty chunky. I can try to do something interesting in here. So just a second, chat. On my other machine, I'm gonna go maybe delete some shit. Maybe delete some shit. Just a second. So there's some stuff I can delete super quick. So, and in here, yeah, now I have a 16 gigabytes. So maybe that's gonna be enough. All right, so I'm gonna go to here. So third party, and let's try to clone this entire thing. Git clone. Depth obviously shallow, right? So because it's gonna be pretty huge project, right? So let's freaking go. So while it is cloning, right? So I'm gonna put the chat in here. Yeah, I deleted the prawn folder. Why Clang instead of GCC? What exactly is this question? I don't understand. Why Rust uses Clang instead of GCC? Go ask Rusticians. Why do you ask me? Too importante. So, all right. Okay, so let's wait until it downloads everything. So hopefully it's not gonna take too much in terms of space, right? So let's actually maybe do watch and one div h, right? So just like look at this thing, and the only thing I need is actually source code, right? So I could have just searched on GitHub, but GitHub search is actual trash. So there's no point in using it at all. So imagine your search being so trash that you can't even compete with grep. God freaking damn it. Anyway, so here's the LLVM project, and what I wanted to do in here is to find the is char signed in Clang, right? So I'm pretty sure just doing a blind grep of this entire thing is not going to be good, though it worked. Look at that. What the fuck? It just worked. Moved to target hook. Right, okay. But that doesn't explain why. I was hoping, god freaking damn it, I was literally hoping that there will be some sort of a comment somewhere there explaining, yeah, so these architectures are like unsigned because that, and that. And they say nothing. They just say, okay, so these architectures are signed and these ones are unsigned. Right, and the comment is fix me. It's an arbitrary historic choice. But what does it affect? What does it even affect? Because, like, addition, if you use two's complement, the addition is going to be the same. Like, what exactly going on, right? It's just like, why? Does it even change anything if the only thing you do on these things are addition? If you multiply two chars, why would you multiply them, right? Why does it matter? So that's just what ARM C standard. There's an ARM C standard. ARM C standard. There's a dedicated C standard for ARM. I thought like C standard is just like a C standard and it's kind of cross-platform. Overflow. Okay. So that's a good point. I forgot about those. Overflow flags are going to be different. That is true. That is actually true, I think. I see. So, and we ended up with this kind of stuff. Damn, that is fascinating, isn't it? Ha. Okay, so, well, I mean, what that means is that now we have to do a conditional compilation, right? So, okay, so we're gonna assume that this is just an arbitrary historical choice. as somebody in the chat said. So let's actually test if just changing the sinus fixes the compilation, right? So we're gonna go into, I think it's defined in crust somewhere. So what we're doing in here, we have this C macro, right? So now let me go and just put U in here, and I'm gonna try to recompile it one more time. And looks like it's gonna succeed, actually, believe it or not. Yeah, damn, is it gonna compile that slow? Oh. Well, technically that fixed it. So let's actually see what the fuck is going on here. Do I have TeamUX? Okay, I do in fact have TeamUX. So can I just rebuild the whole thing? So it's rebuilding everything. For some reason, I didn't expect it to rebuild everything, but it's fine. So first of all, it builds painfully slowly. But second of all, it fails with linking. And I wonder why. Alright, so let's actually go up and see what the fuck is it saying. Something about Musil. Ha. Ha ha ha. Something about Musil. So in function undefined reference to extend dftf2. Alright, that's one's interesting. So what the fuck is this thing? Extend dftf2. So it's something from libgcc. Ha, and we're using Musil. Absolute charging, yeah, so absolute fucking charging. That's me right now. Okay, so the question is, can we, yeah, so what does it even link with? Is it even possible to use, you know, glibc in Musil? So apk list grep glibc. So no, GCC. There's some GCC stuff, right? So we don't have GCC. Ah, no, we do. So, but there should be some sort of a like libgcc. Libgcc. Oh, there is a libgcc. Since it wants this is the stuff from libgcc. It's not really glibc. It's a libgcc. So it's kind of a different library. So maybe this is what we have to add in here. So let's go ahead and just like add and see. Okay, so that was fast, but it's also installed. So maybe it has to be def. No, well, it doesn't even exist. Unfortunately. It's kind of funny that it rebuilds everything. So there's something fucked up with the, well, I mean, this is because it was never properly built. Okay, so by the way, so if I try to Google with Musil, I will probably see a lot of screaming. Yeah, so we will see a lot of screaming in here saying, bruh, it doesn't exist. This is because you use a shady libc. Fuck you. No, fuck you. Give me my function. No, there's nothing like that. Okay. So let's take a look at Alpine. Linux, Jesus Christ, broski. So is there any variance with glibc? Well, I mean, it's called standard. They don't really distinguish it. I was hoping that maybe it's going to be like in void, right? So if you go to void, they give you options to use glibc or not to use glibc. Maybe I should have used like void. Maybe I should have just installed void in here. Right, so if I try to download this kind of thing, so there is a, yeah, look at that. So the live image, glibc or Musil, something like that. It is also for ARM. And yeah, so there is a base for, I should have used void, honestly. Should have used void, not Alpine. Right, so I'm a little bit more familiar with void than Alpine, but I mean, we're already kind of like committed to using Alpine, so it is what it is and it isn't what it isn't. So I thought it's pronounced Musil, or I don't really know how it is pronounced. I'm really sorry about that. I hope I didn't offend anybody. Okay, so what's gonna be the plan? What's gonna be the plan? So we can try to maybe so it's kind of interesting how it's. Is that because we're using Clang in here? Here's the thing. Because we're compiling with Clang, and Clang kind of maybe expects, you know, libgcc and stuff like that. What if we try to compile with GCC in here? Right, so let's give it a try. It's going to be Clang GCC. Right, so boom, boom, boom. So that should be it. So here's the Clang, and all right. So I'm going to try to recompile it one more time. So if it's not going to work, we're going to think how to do something else in here. So Rustlink with GC, not Clang CC would could be any C compiler. Yeah, I see. It still wants this kind of shit, right? So it still wants the stuff from StackCH kguard. So what is this stuff? Is that because maybe so, and it's from Nob, by the way. Look at that. It is from Nob. Maybe Nob is just like not compilable on ARM, but I mean it compiled. So what are we? So this is a static GC, no default. It's all libgcc stuff. Yeah, it's all libgcc stuff, and it doesn't exist on Alpine. Alpine libgcc, right? And well, I mean, it does exist though, but we can't really link with it. Stack smashing detection. So it's a stack smashing detection. Can we disable it maybe? Or can we explicitly link with them? Okay, I have an interesting idea. So where are the flags? Where are the flags? So here they are. So here's another one. Can I just do something like this? What if I just like directly link with this entire stuff? It builds everything. It's a little bit annoying, but I mean, there's nothing much you can do. Diana! Sorry. Diana. Fuck. None of that helped. None of that fucking helped. Okay, so let's take a look at this thing. So maybe if we do Alpine Musil, right? Musil security features. Musil security features. What the fuck is this? It's a latex. Latex glove. No stack protectors. That's an interesting point. Let's give it a try. So let's copy paste this entire. Well, I mean, I wanted to do something like that. No stack. Yeah, so probably has to be without the dash. Stack protector. Right, so it's a singular one. So we're making Rust unsafer. We're making it less safe. Right, so let's go ahead and try to do that. I'm sure this leads nowhere. Like, I feel like I'm wasting time and this leads nowhere, but I still want to try. Maybe I'll accidentally stumble upon something that kind of works. Right, so maybe we'll accidentally stumble upon something that kind of works. So let's put this stuff in here. So f no stack protector, and let's rebuild it one more time. So yeah, I understand that it's kind of unsafe, but our goal is to make it work. Our goal is to make it compilable, right? So if you can't make it compilable, well, we're probably gonna go with a different route. No, it still wants this kind of stuff. So there's also assertion fail. It's all libgcc. It's all libgcc. So yeah, I don't freaking know. I guess we're not going to be doing that on ARM today, right? So we're going to be developing this kind of thing. So here's the plan, chat, right? So here's the plan. Obviously, I'm not going to be like installing Void or anything. So I'm going to like create a new virtual machine off screen. But as of today, I think what we're going to be doing, we're going to be developing on x86-64. Then we're going to be producing the assembly and we're gonna be linking and compile that assembly on emulation on the virtual machine. So that's gonna be the plan. Right, you need to tell that to GCC, not to Rust. Well, I mean, I passed it to the linker, right? So I passed that stuff to the linker, so it gave it to GCC. So sounds Gucci, yeah, sounds in fact Gucci, sounds in fact Tamaguchi. So yeah, that's basically the plan. That's basically the plan. Okay, let's fucking go. Right, and later, maybe in a footnote, right? So I'm gonna just like fix it, and we're gonna try to run the compiler on the virtual machine, right? But anyways, so where we go, so this is B, and we should probably start. And I mean, I plan to develop it on x86-64 anyway, because it's just faster, right? So it's just faster. Let's take a look at the targets that we have. All right, so here I have a target FASM x86-64 Linux, and following the same convention, right? So I'm going to be using gas, right? So if you take a look at what we have in here, so hello ASM. So on the previous streams, we actually explored how to use gas specifically. So here it is, right? So, and because of that, on ARM, we're going to be using gas. Right, so in here we have architecture, so that means it's a arch 64 Linux. So we're kind of developing like a similar to Rust triple, target triple. Meisaka, hello, thank you so much for the raid. Thank you so much. Right, so here's the FASM x86-64 Linux, here's the gas A arch, there's too many A's, honestly. It has to be something like this, or I don't really know. So A arch Linux, right. And after we edit that, we also have to add it to the list in here, right? So this is going to be gas, a arch 64 Linux, right? And this is kind of a similar thing. So gas, a arch. Honestly, I'm not really sure why I don't use dashes in here. I think I'm supposed to use dashes in here. It makes a little bit more sense. So in here we also have JS, and also we have intermediate representation, though I'm not sure if intermediate representation has to be separate target, but I mean, it is what it is. So after that, let's try to compile this entire thing. Right, so, and let's also do B, T, list, right? Right, not to be compiler, but live, yeah, yes. Okay, so gas is not associated, so this is because I did something weird in here. So this is what we have, and when we generate an executable, right, so we have to actually put this kind of stuff in here, and let's actually put to do. It's not implemented yet, right, and there's, yeah, so there's quite a few places where we have to just add this thing. So here's the gas, to do, like so. All right, so generate data section. All of the places where I edit the target, I have to do this kind of thing, but that's fine. That's totally fine. Okay, cool. So now we have several compilation targets in here. So FASM, there's gas, a arch, and the default, I think the default has not changed. Right, so it's still FASM x86-64. Yeah, I accidentally saved the compilation here. Happens. I'm too fast sometimes. So why didn't GNU call it GASM? Yeah, very funny. So let me see if it still works. All right, so this is going to be fib B. There we go. So it seems to be working. It's still working. Okay, cool. All right. So now, what if I try to compile it for ARM? So let me take gas and put it in here. It's a little bit long, but I mean, I don't know how to make it better. Generate executable. Okay, so when we generate an executable, what we do in here, we just like put some sort of a header, right? So for x86-64, it's usually like a format F64 and section executable. To be fair, a section executable should probably not be here, right? So because we have a separate function which is called generate functions, right? So here is a generate fun, actually several of them. So there was, yeah, so generate funcs. I think it has to be somewhere there, right? So because it's a section, right, section where we like all of the functions are contained. So because of that, I have a feeling we have to get rid of that concept completely. Right, so let me do match targets, right? And specifically for FASM x86-64, right? So it's going to be target FASM x86-64. This is where we're going to move this kind of thing. This is where we're going to move. And we also have to do that for the rest of the target as well, right? So the rest of the targets. But for JavaScript, I don't think it's needed, or for IR. So JS, right? It's not gonna do anything, right? So we're gonna keep it like this. Target IR. So if I take a look, generate executable. All right, so for the IR, yeah, for the IR, we probably need to move it there as well. I think it does make sense in here, like so. So because this is the functions that we have in here. And for the gas, not gas, a arch, what we have to do. So let's take a look at it. I suppose it has to be. Yeah, I don't think we have to do anything, right? So because we didn't even use anything in here. Though, we can try something interesting. So I'm going to go into C program, right? So here I have a C program that also does the Fibonacci numbers, which is understandable. Maybe I should create some sort of a hello, right? So let's actually create hello.c. Right, so I'm going to include this stuff. And I'm just going to put something like this. So I'm using tabs, by the way, but I mean, it's fine. Hello world. And what I want to do is just main.c, but I also want to generate assembly out of that. And that created this thing. And usually I don't think we specify any sections. And well, we do specify sections, right? So there's a dot, how was that? Oh my God. Section. So here's this section. All right. So we don't really specify any sections, right? So there's a read-only data. So I presume it just stores all of the code in a read-only section. So that's basically what's going on. Right, that's basically what's going on in here. So I'm really not really sure where exactly we should store all of that. So I think for gas, we're going to just print nothing, right? So in a place where generate functions, just print nothing. For the FASM x86-64, we're going to be doing this kind of stuff. By the way, this kind of implies that maybe we're also going to have a target gas x86-64 Linux, right? So we may use different assemblies and stuff. It said .text. I didn't see it. Wait a second. .text. Where is the text? Ah, I see. Okay, that makes sense. So it's a .text and then section row data. Is that two separate things? Why they are on the same line? I'm not really sure. All right, so here's the arch, arm v8, and so on and so forth. All right, so for now, we're not going to actually put it in any section, right? So we can do that a little bit later, right? So anyways. Okay, let me try to recompile this entire thing just to see what is going on. Okay, so, and obviously, well, you should not put parentheses. This is the worst error that can happen in Rust JavaScript. Okay, let's freaking go. So SB append forgot semicolon. Okay, so now when we generate an executable, yeah, let's not print anything in here. So that's going to be it. So where it failed. Okay. Generate a single function. So let me think how we're going to organize all of that stuff. So maybe we're going to put that in a separate function as well as we did for FASM and stuff like that. I don't know why I keep IR inlined, but for these things I created a separate function. I don't know. Somehow traditionally it happened. A arch 64, right? So, and let's go ahead and create functions for all of that. We might as well maybe copy paste the existing function, right? So just copy pasting the existing function and just using this name instead, like so, boom. And this is what we have to do in here. So essentially, so here, this is that. What we have to do, we have to start iterating through the body that we have in here, and it's a slice, right? So it's a slice. A slice and like a row pointer slice is kind of painful to iterate, but I mean, it is what it is. It's a self-imposed problems. well, kind of. I mean, Rust developers could have made it a little bit easier for me, but they want to maintain safety, so to speak. So this is how we're going to be iterating this entire thing. So here's OP, and we need to match all of these things, right? So we need to match all of that stuff. Okay, so let me see, enumeration OP. So these are all of the instructions that we need to implement, all of the instructions. So I wonder if I can super quickly just do something like this. Just take this stuff, put like this, and then to do, boom. Look at that. Can your Vim do that? Can your Vim? I think it can. Well, we'll also have to do something like OP, colon. All right, so we got some other stuff. Yeah, all of that is unused. So for now, I think I'm gonna just disable all of these things, right? So allow unused variables for this thing, and everything seems to be working. Okay, that's cool. So then when we generate external symbols, this one is also rather interesting. Generate externals. I think it went too quickly on externals, because externals are generated at the end after generating all of the function. Yeah, so we did generate funcs, right? So we did generate funcs, and then we iterated generate a new function, and we do that. So I would expect this thing to actually crash at here, right? Aha, this is because I fucked up. Okay. So I'm glad that I looked into that, because that's a huge mistake in here. That's a huge mistake. Okay, so auto assign. So assignment of the variable. Assignment of the variable. So to do an assignment for the variable in x86 in ARch64, we need to understand how the freaking stack works in ARM. So that's kind of interesting. So let's take a look at what we have in here. So here we have an index and an arg. That's what we have in here, an index and an arg. An index is the index of the variable on the stack. Variable on the stack. An arg is actually can be all sorts of things. Arg can be all sorts of things. So let me actually see. It could be another variable on a stack. It could be literal, or it could be a data offset, right? So we have a data section where we store the string literal specifically, and this could be an offset within that section, right? So it usually happens when you're trying to pass a string literal to a function call or do something with string literals. In this particular argument, you're going to have data offset. So, and yeah, that's an interesting question. So let's take a look at what we can do in here. For instance, we can try to, yeah, I think the easiest thing to do in here is to use assembly in GCC. Just like write some C code, generate assembly out of that, study that assembly, and then adapt that assembly to the, you know, to the B compiler. So that's what we're going to be doing. And here's an interesting thing, by the way. This is kind of philosophical, right? So people complain that like LLMs will make younger generation of programmers stop learning programming, because there's no point in learning programming, right? You can just ask LLM. But if you take a position of LLM being just, you know, a new programming language, which is basically stochastic non-formal programming language, that may not even true. You can compare it to the compilers of today, right? To the compilers of today. By that logic, compilers should have stopped people from learning assembly a long time ago. But people still to this day ask compilers to generate assembly, then they study generated assembly, and then they use the knowledge to produce a new assembly that the compiler can't really produce itself. I predict, right, so with a certain confidence, that this is what's going to happen with LLMs as well. A lot of people will not study programming, and that's fine. Not everybody needs to be a programmer. That is true. Not everybody needs to be a programmer. But there will be quite a lot of people who just ask LLM to generate the code, and then they're going to be studying the code to produce something that LLM can't really produce. Similarly to how today, even right now, we are studying the output of the compiler to understand what it's doing, so then we can transform that knowledge into something new. So I think that's what's going to happen. So what do you guys think? Banger. I agree with that. Okay, so let's fucking go. Penga! Jomon Penga! Ooh! LLMs can only generate what we as functions has created once. Not really true. Right, so they can... If you think about the training data as points in a function space, LLM is just a function that tries to meet all of these points. It tries to interpolate all of these points. And between these points, in the interpolation, you may encounter something that humans have never written. Right. So, because it's going to be a combination of like 2 points, something like an average of these 2 points. But at the same time, an average of 2 points is something that human could have easily produced anyway. Right. So, the job of the human is to find points outside of that manifold, if you know what I mean. That's kind of the job of the humans, right? Does it make sense? So, yeah. And that's why it's so easy to use LLMs for copyright laundering, right? Because you can easily argue, oh, it's produced something novel, when in reality it just took an average of 2 points, which nobody done because nobody fucking needed to. Like, it's like, yeah, so... right, so... You know what I mean? So, yeah, let's fucking go. So what I want to do, like, I don't like that it uses tabs. I think I need to configure, I need to rise my Vim, chat. I need to rise my Vim. So let's fucking go. Vim RC, what we need to put in here? I need to take a look at my current Vim configuration. So Vim RC. So tab stop 4. Okay, so that's one thing I probably need in here. That's a lot of shit I have in here. So shift tab width 4. So this is 1. GUI. I used to use GUI, yeah, so I used to use GVim, apparently. Relative numbers, by the way, this is something that is very useful. Ignore case, smart case, increment search, this is also very useful stuff. Yeah, this one is for C. It actually makes it behave normally with switch cases and stuff like that. Oh yeah, I also have a Russian keyboard thingy. I mean, that's fine. Auto indent. I don't remember what these things are, but might as well just like put them in here. Anyway, so I think this Vim is going to be a little bit better now, hopefully. This is not what I want to open. I want to open hello. Yep, so this is tab, and if I re-indent, yeah, so this is tab, little spaces and stuff like that. What is smart case? I don't remember. So, like, don't expect me to know any of these options. I just collected all of these options throughout the years by Googling stuff, and like, I don't freaking remember. So, smart case, let's take a look. Yeah. Override the ignore case option if the search pattern contains uppercase characters. Only use when the search. Oh yeah, yeah. So essentially, so I suppose maybe it's something like this. Freaking yeah. So if I search, for example, for main, right? So this is a lowercase one, but it still matched the uppercase one, and it jumps between all of them. I don't remember, I think it also works with substitution, right? So if I do main entry, nah, it didn't. Well, I mean, I have to kind of do something like this. Yeah, so I don't remember. So I was looking for an option that would also replace this entry with a capital entry, right? So something that Emacs does, but I don't remember. Yeah, it's for search, okay, so it's not for replacement. But anyway, right, so here is the stuff, and if I do... So what I want to do, by the way, chat, I want to just allocate something on a stack. So we can do something like maybe like sum. Right, so here is the A and B. And what we want to do here, we want to kind of allocate C, which is going to be A plus B, and then return C. Doesn't automatically indent things. Do I have to do something for indentation? Yeah. So file type indent on auto indent. I think I enabled it, but whatever. All right, so let's do ccs hello.c. Right. So, but also let's do O0 to disable all of the optimizations. Let's take a look at the hello s. All right, so here's the sum, and okay, so that's how we do that. So you subtract Man, that is actually super easy. Right, so so you loading, so this is LDR, so STR. This one is interesting actually. So we'll need this, by the way, for allocating things. When I generate function, right? When I generate function and generate specifically FASM x86-64, right? So this function accepts how many automatic variables we have to allocate at the stack. So I actually implemented this thing where we do not constantly allocate temporary variables. We actually compute the maximum amount of temporary variables that we need, and we only allocate that at the beginning of the stream. So we're finding the height of the DFS tree. I implemented that. It's already implemented, by the way. Not even joking. So we can try to maybe look into that. So I can do IR on Fibonacci. Fibonacci, like IR is not runnable, but I mean, it should work. Okay, so generated file, right? So, yeah, so it doesn't even print that. AR doesn't even print that, but let's do just FASM x86-64. I have to do in here. And if I go to assembly, where is the assembly? So it's somewhere here. There we go. Look at that. Right, it just does sub once. Right, it just does sub once and that's it. And it just reuses these variables over and over again. It's so cool, the amount of registers has. I'm sure it will make some stuff way easier. Yeah, as already said, I was thinking to actually maybe store automatic variables in the registers. Right, so... But I mean, do they get clobbered? Yeah, so it's kind of difficult. Like if you do function call, right, so you have to be a little bit careful. Does B support VLAs? I don't freaking know. Right, so if we take a look at the spec, right, that is written by Ken Thompson. So arrays, first of all, in B are called vectors, right? They're called vectors. So, and there's a vector declaration, a vector definition. So an external vector definition has the following form, right? So, and I think you only can declare them outside of the functions. There's some examples in here which use vectors, and vectors are explicitly defined outside of the functions. And then they're used inside of the functions also by declaring them as external. I don't remember anywhere in the spec that you can do that inside of the function in the stack. Yeah, so only static arrays, right? So, which actually makes it a little bit easier. Right, so the semantic of B makes a lot of things easier. The fact that all of the variables, they all type word, makes it super easy to allocate and deallocate them on the stack. It's actually kind of cool. I really like this language. It's less powerful than C. It is definitely less powerful than C, but at the same time, it is easier to implement. It is way easier to implement, and I would argue that B is the actual cross-platform assembler. Right, so people call C the cross-platform assembly, but no, B is actually cross-platform assembly because it's kind of semantically closer to assembly. It's semantically closer to it. So yeah, it's kind of an interesting language. Kind of interesting. I'm actually glad that they decided to go ahead and implement it. Does B have pointers? Yes, but it doesn't have any specific types, right? So it's just like the pointer is not distinguishable from just a regular number. That's the thing. So you can store a number and there's an operation of dereferencing. So what that means is that if in a variable you have a particular number and you say dereference it, it will just treat it as a pointer. So it doesn't do any type checks or anything. It's just like, yeah, so there is a pointers, but I mean, everything is a pointer if you're brave enough. So get some subs, right? So thank you so much. Disturbed Waffle with a message support for Panger machine. Thank you so much. AL Handy, thank you so much for the sub with the message smiley face. Strawberry Starlight, thank you so much for the sub and the message. Hello, Mr. Zodi. Question: how pain in the ass would it be to develop a front end for GCC for B? I have no idea. Probably a huge pain in the ass. somebody, I think some message flew by in the chat that the answer is very GCC is a trash code base. And it's said by this Houston. I suppose he knows what he's talking about, right? So yeah, it's probably huge pain in the ass. GNU moment, yeah. As remember, in one of the conferences, RMS Stallman said a very interesting thing. He said that simplicity of the code base is not a necessary requirement for free software. I don't remember the context, but it's just like, when I heard that, it's just like, oh, so that's why all the GNU code bases are such trash. So because it's not a necessary requirement for the free software. That explains a lot. So now I understand. Now I fucking understand. Which I think kind of contradicts to the values of free software. It kind of contradicts to the value of free software. Right, so because it has to be open source. You can make any open source software closed source by making it complicated and convoluted enough. Right? How is that not necessary requirement of free software? You're supposed to be in control of your software, so that means you're supposed to understand what it does, so you should be able to modify it. By making it convoluted and complicated, you're stripping away the user from their right to modify software and understand what software is doing. So what the fuck? So, I don't know. He's so obsessed with the reputation of free software because open source software store all of the limelight, and now everyone is talking about open source software, but nobody's talking about free software, because free software is not only about open source, but it's also about the freedoms. Well, you're fucking taking away the freedoms with this kind of shit. Excuse me. So, but I don't know. I haven't studied his position about that, like, with more details. Maybe I'm incorrect about understanding of his position regarding that. But again, it's just like, I think simplicity of the code base should be one of the requirements for free software. Because again, it gives you agency, it gives you freedom, right? So because you're capable of understanding it, right? So yeah, that makes sense. But again, like, how do you define simplicity? But at the same time, how do you define freedoms in free software? It's also all muddy and gray area. Anyways. I already streamed for 1 hour. I think I need to make a small break. I need to make a cup of tea. Right, so let's go ahead and make a small break. Make a cup of tea, and after that we're gonna continue porting it to ARM. We're back. Let's freaking continue, my friend. So, all right. So we need to do this kind of thing. I already closed the example. Hello, and here is our hello s. But this is, oh, wait a freaking second. Do I have, I think I have, yeah, TeamUX, there we go. So I have a TeamUX connection here. So what's the easiest way for me to do this? I need to read. I suppose we're doing LDR. You know what? I feel like I need to start with simpler example. I'm trying to actually port a very difficult example. Right? It's not a good idea. It's not a good idea. So let's start with foo b, right? So with foo b, which is just main, and it does nothing. Just does nothing, right? So I think it's fair. And I'm just trying to build foo with the target ARM. Let's take a look at the list. Here is the gas, and I'm gonna put this gas in here. Look at that. Okay, and it doesn't work. So generate externs. How do we generate external declarations? That's a very interesting question. So we are here calling printf, don't we? Do we call printf? We actually don't. That's very interesting. So let me take a look at the C. This is not what I want to open, Bravsky. Yeah, we do call to printf. But what about this one? I don't see printf. So did it get optimized out? It calls to puts, get freaking, okay. I hate when it does that. I really hate when it does that. And it doesn't even externally declare it or anything. So it just calls puts. 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 Interesting. So BL puts. Let's open maybe ARM documentation, ARM reference manual. Install QEMA. So there was a reference manual somewhere here that we used. I'm pretty sure it's somewhere here. It's this one. So in the previous streams we actually had it. So what is BL? What is BL? HTML. I don't see the description. Branch with link branches to a PC relative of set. So it's basically call. Calling is branching, but does it put something? It provides a hint that this is a subroutine call. Ah, interesting. So it's a branching, but it's okay. So it's a subroutine call. Very interesting. Very interesting. So that means to just call a subroutine, I have to do that. So I want to try to maybe have something like foo s, right? And in here, what we need is this thing. But on top of that, I'm pretty sure we need to declare this thing global. Right, so then we just call puts like so. And how do we return? Oh, then we just return from that. Okay, so that's pretty cool. Might as well close. And in here, I'm gonna do as foo s. Right, so it finished successfully, and it created a out. You probably didn't see that, but it created a out. I can try to do that one more time. So let me go here. So here's a out. So, and what should we probably do instead is use o, foo o, like this. Well, it might have actually. Did it create O file? If I take a look at O, it's relocatable. Okay, so that means in here I can now try to do foo O, and then I can try to do that. It's segmentation fault, but it's kind of expected because I didn't provide anything. So to use external symbols, you don't need anything, right? So this is what I was trying to check, right? Because in FASM, right? So if you use FASM, you have to declare each and individual external symbol. That's something that you have to do. In here, you don't have to, but what we do have a list of external symbols that the program is using. We might as well maybe print it somewhere as a comment, right? So for example, if you compile it to JavaScript, we put it in a comment somewhere. So what are the comments for this entire thing? So if I take a look at the vim foo s, right? So I can, yeah, it's probably C comments, right? So something like test. So then in here, it's as O, let's put it like that, and it seems to be working. Okay, so let's go ahead and just like print all of that stuff like this. We can even, it's kind of similar actually to JavaScript. It's literally the same. Wait a second, I might as well. Isn't that funny? How for that specific case, like gas, Arch Linux, and JavaScript, it's literally the same. So there's no difference. Wait, doesn't ARM have a JavaScript instruction? ARM JavaScript instruction. I completely forgot about it. It's this one. Oh, for fuck's sake, I can't open it, but it's a floating point JavaScript convert to side fixed point. Bro, ARM is JavaScript confirmed. Like, absolutely confirmed. So it's a chip that can interpret JavaScript. Beautiful, but will confuse the heck out of you in the future. You really underestimate me. Okay. So generate externs. So we established the externs. Cool. So what else do we have in here? So generate data section. This one is interesting. So how do we generate the data? So let's go to foo s. Well, I mean, yeah, we're already there. I want you to go to maybe hello C. It's kind of difficult. Let's go to hello C. All right. So for now, let's comment out this entire thing like so. All right. So now let's do cc o0 generate assembly and just compile that. There we go. So what do we have in here? So hello s, here it is. So let's open hello s, and that's what we have. So you just have string. But, and this is, by the way, how we do the label, right? So this is basically the label, and we can see how this label is used. Yeah, so it's just used like that. What if I have some arbitrary data? Because this is supposed to be arbitrary data, actually. So let's go to hello C, and let me put something like, I don't know, x69, x34, x35, and stuff like that. And then let's go to here. All right, and let's reopen hello.s. Okay, so string I for so, but this is because all of these things are ASCII, right? So we just converted this to ASCII I for fun. Well, I mean, it has to be even, but it's hex, right? So 69 is decimal, right? 69 is decimal, but this one was actually hex. Right. Let me go back to hello, hello C. So let's actually put something like maybe 0, but I hope it's not going to optimize it out. So we can put something like 1, 2, 3, 4, and let's fucking go. So, and hello.s, hello.s. Okay. Is that, what is it called? Octal. Bro, like the only thing I want is to trigger this motherfucker to output hex. So I just want to confirm that it's /x. Why are you so fucking, just output hex? So so there is a .byte or something. Okay. But I mean, I just wanted to trick it to do something, right? So I just wanted to trick it to do something. So, well, I mean, I don't know. I don't freaking know, Brovsky. I don't freaking know. Okay, so also here we just do that. So we put some stuff into puts. Add RP. So what is add RP? Let's close this stuff. Add RP. So from PC relative address adds an immediate value that is shifted left by 12 bits. That's weirdly specific to the PC value to form a PC relative address with the bottom 12 bits masked out and writes the... What the fuck am I reading? Excuse me? Okay, so can I just like risk my ass? Is that something from risk? Why exactly 12 bits? I don't quite understand. Why? Yeah, I don't know why 12 bits. That's bizarre. But I suppose this is how it works, right? So if I do something like foo s, right? So if I do something like foo s, and the way here I can just do, I don't know, message, right? So might as well just do something like this. And this is going to be string test adrp x0 message, and then I do bl puts. So after that, hopefully, if I do something like, it's actually really slow. So where is s? Oh yeah, here it is. There we go. So might as well maybe create a makefile. Do I have a makefile? No, I don't. So foo depends on foo o, and in here we just do this kind of thing. Foo o. Foo o. Could you please freaking indent it properly? Thank you. Foo s, and this is s o foo s. Right. So then I can do something like this. Make. All right. Missing separator. Are you stupid? I said tab. Oh. No expand tab. Yeah, I think I forgot to no expand tab. Yeah. But at the same time, I think, like, why did it work on my machine in here? So what's up with that? Tab, no expand tab. Ah, for some places I actually, okay. All right, so let's go back to makefile. So no expand tab. Yeah. All right, so now it is working. All right, so can I make it now? It seems to be working. So now if I do something like this, it command terminated. It didn't do shit. Didn't actually do shit. So foo s, so that didn't work. That didn't work. So let's take a look at hello.s. So this is a string lc0. So I remember it did some additional things. Yeah, so it does that, then it does additional thing. My question is, why can't I just freaking move this thing to here? Can't I just move it there? Like, why does it have to be this weird ass shit? Is that something GCC just like shed it out, or is this necessary? Like, it's kind of weird, not gonna lie. Right, so why am I doing it like this? And it worked, and then I can do foo. Okay, so that didn't work. So that's still boss error. P64 don't fit in a single instruction. Interesting. That is very interesting. So hello.c, .s actually. So we have to do this kind of thing. What is a low? Ah, it's a low 12. Ah! So you add RP, then you add... Oof. I think I understand what is going on. So address 4 kilobytes adds immediate value that is shifted by... It's shifted by 12 bytes? Right, and then we add a... Oh my god! I think I understand. Because it's just like, you load an address of this thing in chunks. Oh my god! 12 bits, I'm sorry, not 12 bytes. Thank you so much. 12 bits. So this loads like first chunk and this loads another chunk. Holy fuck! Oh! What the fuck? Assembling an address bit by bit. What? Woo! Let's fucking go. So it's first loads the 4-level paging and then the address. Yes. Apparently. Oh boy. Oh boy. Oh boy. Okay. So that's interesting. Well, we're learning things, right? Again, we're learning things. So then I add x0, x0, the low 12, actually MCG, right? And then we'll just do that. Boom. And then I do foo. Yeah. So command terminated, and it actually didn't really print anything meaningful. Might as well maybe put new line in here. So let's try to put a new line in here. So this one has to be foo. Still isn't pretty shit, but let's actually try to run this thing. So bus error still. So bus error still. Okay, foo s. Okay, so and so hello s. Interesting. So is that because that's yeah, it's a raw data. Ah, this one is interesting actually. So this is a text section raw data, and this is another text, but it's a global. Maybe that's why. Align 3, look at that. Right, align 3. So that's what it's doing. This align 2. So maybe this is something about alignment. That could be it actually. Interestingly. So because I do remember ARM was like very annoying about alignment. Like at least this is what I heard. You need to align main. Yeah, looks like it. So we can try to do this kind of thing. So this is a global. Well, I probably have to put it in here, right? So this is global. And align 2. Right. So do I have to? It's kind of interesting. So this is just things by themselves. I need some sort of reference manual for gas. GNU as reference manual. GNU as reference manual. So table of contents. Can I just search for things like .align? I can. Look at that. Okay, so that's pretty cool. Pad the location counter. Okay, location counter in the current subsection to a particular storage boundary. The first expression, which must be absolute, is aligned required as described below. Right, and in this specific case, right, they align by 3. So, and it's in bytes. It's a storage boundary. Okay, so the, for example, align 3 advances the location counter until it's a multiple of 8. But why 3 though? So absolute expression, absolute power. Ah, it's a powers of 2. Okay, okay. So that explains it. So might as well. What if I just align these things as 3? Ah, I see now. I think what we have to do in here is just like we have this at the beginning, and I suppose beginning is kind of aligned. The beginning is kind of aligned, and then we say, okay, find the next boundary that is basically power of 2 to 3, right? So basically 8, and this is where it starts main. Okay, that explains why it was a buzz error, right? Because so we tried to execute the instructions that were not aligned, so we just like executed some sort of a garbage or whatever. Okay, so I think if I understood everything correctly, just putting .align 3 in here should be sufficient. I think this should be sufficient, so let's actually give it a try. So only if this thing is aligned. We have to be careful because it may not work because this thing is not properly aligned. But I kind of suppose that maybe the beginning of the file means that everything is aligned properly anyway. You know what I mean? You know what I mean? I think it should be it. Okay. So let's try to make this entire thing, right? So and then I try to execute foo. It worked. Okay, so the beginning apparently is aligned properly, and then the next thing we have to align to the boundaries of 8. Okay. The string, yeah. Okay, so that seems to be working. Okay, I'm understanding. I'm learning things. That's very cool. That's very cool. All right, all right. So that's kind of poggers. That's kind of woggers. And by the way, so what I want you to do, I want you to test some things, right? So can I just put like, I don't know, x69, right? And then x34, x35, and then just like a new line, right? So because I have just data section with bytes, just a data section with bytes, and I want to output them in the most convenient way so I don't have to escape anything, and just hexadecimal looks perfect to me, actually. Right, it actually looks perfect. 2 should be enough. Well, maybe, yeah, I know. Okay, so let's actually try to do that, and let's execute foo. And it's I45, right? So which is precisely what we expected in here. So we also have to terminate ourselves, which is that a what is it? Vim thing? Look at that. What the fuck is this shit? I know what the fuck is this shit. Who knows why? Who knows why it does not terminate automatically for me? Who can guess? It's actually, I think it's very easy to guess. Is that the reason? Let's give it a try. Let's give it a try. Oh no, it's not that. Okay, it's fine. So I don't know then. Well, I mean, 0 is kind of probably needed. Syscall exit. But I mean, we return out of main. We return out of main, so that shouldn't be it. So ret in... Okay. So ret in main is based on registers, not stack. Oh, fuck. Okay. So, all right. So let's take a look at what we have in here. So it's hello s. Yeah. And return, let's take a look at how you do a ret. Oof. So the return address is located on the stack, at least in case of GCC. So you need to load this thing to one of the registers, so then you can perform the return. It's to 30, okay, but I mean it also does x29 or something. So let's take a look at LDP then. So I'm gonna, can I duplicate this thing? Yeah, there we go. LDP doesn't exist. Nice. Do we have a list of instructions anywhere? LDP. LDP underscore gen. Thank you very much. Load pair of registers. Calculate an address from a base register value and an immediate offset. Loads 2 32-bit words into 64 double words from memory and writes them to 2 registers. All right. So that's a lot of things in here, right? So, and it also uses x29. Okay, so it moves stack pointer to x29, and I suppose this is kind of a normal prologue, right? Okay, so we're kind of saving the stack pointer to x29, right? So we're saving it. We do some shit. So this is subtraction, if I understand correctly. STP is saving. Right. I don't know how to properly duplicate this thing. So STP, fuck, it's not STP. STP, store pair of registers, calculates an address. Okay, so it's store. Okay, so it's basically an opposite operation of LDP. That's very interesting. So we do that, but I feel like we should not subtract anything yet. Right, so because we don't allocate anything on the stack, right? So we write some stuff in here and we move, yeah. So this is prologue. And then we have some sort of an epilogue in here where I'm not really sure about W0. I suspect that W0 is the exit code that we return in here. My brain is bleeding. That's normal. I don't understand shit either, but that's kind of the point. We are trying to understand things. All right, so I'm gonna try to just basically, So, and we essentially allocating that stuff back. Yeah, so it's a return address. I see. So here we had. But to be fair, we were not allocating anything on the stack either, so maybe I should have done -16, right? Right, so that's basically the empty prologue and epilogue without allocating anything on the stack, because we really do not allocate anything on the stack. Okay, so there's a lot of this kind of stuff, but I suspect that it's not needed that much, honestly. All right, so this is something that we need to understand. I think the shadow space required on ARM stack is 16 bytes minimum. I see. Shadow space. Terminal make. All right, so that at least compiled. And that's terminated. Interestingly, so let's remove 0. I don't know what I'm doing, but I'm not sure if we need 0 in here, right? So, but we explicitly said string. Right, we explicitly say string. Maybe because of that, it's gonna, you know, automatically append it. By the way, new line. Right, so we don't need new line because I think puts actually put the new line. So let's take a look at the puts. The puts. The puts. So writes a string as and a trailing new line to std out. Okay, so we don't need to do that. That's cool. And now, if I try to compile this entire thing and foo. So it's I45 and with no extra new lines or anything like that. I'm still not sure about dot string, but we can always just look at the documentation. Right, who said we can't do that? We can do that. That is fucked up, but dot string. Okay, so copy the characters in string to the object file. You may specify more than one string to copy, separate by comma, unless otherwise specified for a particular machine. The assembly marks the end of each string with 0 bytes. Okay, you can use any of the escape sequences described in section string. Okay, that's cool. So is there bytes? People said that there is bytes. The bytes. All right, so this is the bytes. Expect 0 or more expressions separated by comma. Each expression is assembled into the next byte. Fucking show me examples, or like what do I put in there? I don't fucking know. So that's kind of bizarre, but we can just try to experiment. So this is bytes, and in here I suppose 69. 34, 35. In fact, I would like to maybe put 69 at the end in there. Right, so I know that it's actually distinct from the rest of the stuff. Okay, so if I try to make junk at the end of the line, recognized character 0. So yeah, it probably has to be some hash or whatnot. So let's give it a try then. 34, and it's probably not hash. Oh, it's not even that. Okay, so let me take a look at hello s. Yeah, I don't see. So main s. There's a lot of things. It doesn't work. So it was comma separated. Yeah, separated by commas. Let's try to maybe, I don't know, put something like this. Okay, GNU as .bytes example. Why is it so freaking difficult to provide like a simple goddamn fucking example? What is this gatekeeping? It's probably something dumb. Like I swear to God, but it's a single byte. It's a single byte. There's no bytes. Who suggested bytes? It's useless for us. So you can only specify single byte, or like, I mean, I don't know. Just a second. Yeah, so example, instead of thousands of freaking documentation, just a fucking example. Okay, so it's probably 0x. Man, I mean, I hate this kind of shit, honestly. Something that could have been a single example, I just like, oh, it's, yeah, oh my God. And the error messages are absolutely fucking useless. Okay, so not reference. All right, so what the fuck are you saying? So it has to be MCG like that. All right, and then if I try to run it, okay, but this one is probably not null terminated, so we have to terminate it ourselves. Finally, so that was more difficult than I expected. Like, come on, this is stupid. This is what we need. Yep, this is what we need. Exactly what we need. So we put actually data somewhere at the end of this entire stuff. So which means, yeah, we have to do something like this, but I'm not sure if it's going to be aligned. Right, I'm not sure if it's going to be aligned. If I try to do something like this, make, so that works, and if I try to run it, that works as well. So and we don't even have to align it. Right, so do you understand correctly that this, how is that called? strings don't need to be aligned. Well, I mean, we had to align it. So do we have to align this thing? So because all of the instructions there are aligned, they're the same size, aren't they? They're the same size. So if I put some data right after the instructions, do I put it on the right boundary, on the right alignment boundary? Does anybody know? 4 bytes per instruction. Thank you. Okay, so that means I really don't need any alignment in here. Cool. So now, finally, I gathered all of the necessary information to generate a data section. Thank you, everyone. Let's fucking go. So I was, the entirety of the time, I was gathering information. How the fuck do I generate a data section? Now I know. So that's pretty cool. So let's go ahead and do that. So funnily enough, like in this case, we're generating data section only if we have some data, right? So data is actually just an array of bytes, right? So what I need to do now, I just like need to generate this thing in assembly. So that's basically it. That's basically it. So if we have some data, what we have to do is probably sp append output, and here we can do something like dat byte, and yeah, that's about it, I suppose. So just byte, and then I put space in here. I think that's a good idea. So and after that, I feel like, yeah, I feel like I can just do that. I feel like I can just do that. And also a new line at the end of all of this. So yeah, so that's basically how we're going to be generating this section. It would be nice to kind of wrap it around, right, but I don't want to spend too much time on that. And we don't really store that much data where it would be needed. So it's only needed for humans, right? So it's not needed for the compilers. Okay, so what do we have in here? Ooh, this one is interesting. So now it fails at generating the final assembly. So let's actually try to do the following thing. Okay, so when we're generating the final assembly, we're actually computing the effective output path, because recently I made so the -o flag is optional because it computes the output path based on the input path. Right, so what it does, you didn't provide any output path, it tries to strip away .b. If it manages to do that, that's the effective output path, the final executable path. If it fails to do that, that means it's not .b, and I just like use a different extension in here, right? So for the convenience, I'm not really sure if it's a good idea, but whatever. So we're going to be doing the same thing in here, right? So we're going to be doing the same thing in here. I will compress it a little bit later. So based on that output path, we're also generating an assembly, and I suppose for now, the idea is we're going to just save that assembly to the file system. We're just saving it to the file system. Okay, so let's actually save what we have in here, and let's try to compile this one more time. All right, so, and in my opinion, by the way, it should not be awesome, right? It kind of, yeah, it generated nothing, literally nothing. So that's kind of funny. Is that because it should have generated at least like a main function. So that's a little bit sus. That's a little bit sus. But first of all, I think the extension it should use the S extension, right? So because we're using GNU assembly, so it's a S. So let's try to do that, and there we go. So on top of B, it generated S, and it only printed external symbols that we didn't have in here. One of the things we can do, we can just say extern symbol printf, right? So let's start with external symbol. You forgot generate func probably. Yeah, well, I mean, we can troubleshoot that later. Doesn't matter. Okay. So here is the bunch of external symbols that we have in here. Okay, so let's take a look at what exactly happens in here. We try to generate program, right? We try to generate program. We generate the executable, then we generate funcs. All right. We generate funcs, and in gas, we just don't do anything, and then we generate function, where we also generate this kind of thing, and I would expect this thing to fail. I would expect this thing to fail, but it didn't fail, unfortunately. So that's kind of bizarre, in my opinion. So let's put some, so we actually put like gas in here. Well, yeah, so that should work. I don't really know why. So, so it's a new line. I'm gonna put this stuff in here. And yeah, let's fucking go. And yeah, so it didn't call, because I see. The body is empty, right? So body len, right, body len. And when I generate a function, a specific function, I have to provide, yeah, I have to provide the prologue and epilogue and stuff like that. This is something that I forgot. All right, so we figured out what's up with all of that. That's cool. So, and this is going to be our prologue essentially, right? So let's actually split the screen and let's start copy pasting whatever we discovered so far. So let's be append. So this is the output, and we just have to provide the global main and so on and so forth. So this is going to be global, and we have to provide the name. The name of the function is this. So here is the name. So this is a new line, and this is name. Okay. So then we provide just the name, like so. So then we have this prologue, right? So we're gonna just like use the same prologue for all of the functions. I think that's fair. So what do we have in here? Might as well copy paste it, because why not? I'm not sure about this exclamation mark. It's kind of sus. Right, so let's put this stuff in here. So this is new line and 4. For this one, I think I may type it out myself. Move x29 sp. So this is a prologue, and we now need to specify the epilogue. Can I copy paste the entirety of this thing so then later I can just like this? Look at that. That's pretty epic. I think that's pretty epic. So I'm going to do something like this. It's a C, like so, boom, and we can do sb append to the output, like so. But then at the end we need to put a new line. Boom. Look at that. So this is what we're generating for each individual function, right? So the body is empty, so there will be nothing in there, but that's besides the point. So for each of them, I also feel like we need to print the label, right? So kind of similar to how we do that for x86-64. This is JavaScript. For x86-64, we just like print this kind of stuff. arch64, like this. And we also print this thing at the very end. Right, and it's needed for the, you know, conditional, unconditional jumps and stuff like that. So this is what it's needed for. Here is body len. Okay, so let's try to recompile this entire thing, and it seems to be working. Might as well maybe output, well, I mean, it will try to create a weird assembly. But anyway, so let's open this thing, and here's the main. So I forgot, you know, tabs or indentation for some of these things. You know, arch64. So Linux function. So here it is. This is what I forgot. Like so. All right. So foo.s. Let's go. So this is what we got. Pretty cool. It's pretty cool. Pretty cool. Prologue and epilogue. So what's up, Aiden? How are you doing? You're welcome for this pure and filtered genius. Yeah, thank you so much. Okay, so now I need to maybe somehow test it out. So I probably want to copy that to my virtual machine. So let's actually go somewhere here. So we don't have anything special in here, and I'm going to do scp foo.s port. I think scp actually has a really weird port situation. Yeah, it's a capital letter. So scp port 22, and I'm copying foo.s to root at localhost, just like that. Okay, so that's pretty cool, and there's nothing. Yeah, that is bizarre. You didn't copy shit. Yeah, okay, so it's not localhost, it's 127.0.0.1. Password bonding. Ah, fuck. Emacs, fuck you, Emacs. Okay. it doesn't allow me to just do this, so that means I have to do some stupid shit. But I might as well, yeah. So I probably should use tramp thingy. Okay. So I don't remember how I use tramp, so I don't want to use it. Let's go here and scope paste it. Finally, get some stuff. Get some stuff. So here it is on the ARM virtual machine, right? Like this. And as o foo.o foo.s, it compiled. So we've got this thing. And now I should be able to maybe do foo, not really ld, but foo.o. Okay, and it didn't do anything, and it didn't return anything special, right? So it's a 0. We might as well actually ask it to return a different exit code just to test how all of that works. Right, so the s, then cco, foo, echo 69. But I mean, we had to directly modify the assembly to achieve that. One of the ideas that I have right now, what if in foo.b we do extern exit and I directly call exit, I don't know, 34. So that way, we're gonna test linking with external functions plus passing, you know, arguments to external functions and stuff like that. So this is the next step, right? So the first step is compilation of an empty function, empty program that passed. We managed to do that. Now let's compile a function call, a single function call. So we are making progress, chat. We're actually making progress. There's no types in B. Yeah, there's no types. Everything is considered like a word. So what the fuck is that? All right, so let's try to recompile this entire thing and see where it will fail. Okay, perfect. So it tried to do a function call. It tried to perform a function call. So in an OP fun call, what do we have in here? So we have quite a few things, honestly. All right, that's understandable. Yeah, so we have result. It's where we're gonna store the result. So we also have the name. So what kind of function we're calling, and the arguments. All right, so that all is understandable. That all is understandable. So let's freaking go. Oh boy. So let me maybe go back to experimentation. Back to experimentation, and that experimentation was in. I forgot where it was. Actually, it was in hello. Yeah. So foo.s. If I go back to maybe hello.s, how do I pass arguments to the function call? So here I put, yeah, so this is how we pass the arguments. Here's how we pass the arguments. But if I want to pass some sort of a number, how it is going to work? We can give it a try. I can go to hello.c, right, and I can cheat a little bit. I might as well just call this thing directly, right, and just see how it does that. So first 4 args go into x0, x7, and then you pass them on the stack. Okay, thank you so much. That actually aligns with whatever we see in here, I think, right? So because x0 is the first argument in here, and we're trying to compute this kind of thing. So I don't think we need it right now, right? So because we're trying to pass like an immediate value, I suppose we'll need it when we need to pass, you know, address from the data, right, from the data section. So at some point we're gonna do that. Okay, so I want to go to make file and just do the following thing. So hello.s is gonna depend on hello.c, and yeah, set no expand tab like this, and it's gonna be just s0, oh, 0 I said, hello.c, and let's do terminal make hello.s. All right, so well, I mean, let's do the following thing. It's taking some time to open this prompt. Okay, so you need stdlib. That's understandable. Hello.c. So let's include stdlib.h. All right, so that seems to be working, and now I can open hello.s. Oh, Is W0 an alias for X0? Oh, it's probably similar to EAX and RAX in x86-64, right? So 32-bit. So W0 is like, which one is 32-bit? W0 is 32-bit, X0 is 64. Okay, that makes sense. So in that case, I suppose, yeah, we can just store that into X0. All right. Okay, cool. So how we're gonna be approaching this entire thing? I suppose we can just have registers similar to this, right? So this is registers, and so the first 8, you say, x0, x1, x2, x3, x4, and so to do add the rest of the registers. The first 8 args go to x0, x7. So that's basically what we're doing here. On top of that, we need to check that we provided enough arguments, and in here's an interesting part. We just pass all of that stuff in here. All right. So look at that. So for now, we're passing literal. We might as well just put to-dos in all of these things and just let them fail. So which one fails, that's the one we're going to implement in here. That's the one we're going to implement in here. So by the way, on top of that, like, we can go with this implementation for a very long time. We need to define a scope. How much of ARM support do we implement? So I think in this single session, I will implement enough ARM support to run the Fibonacci numbers example. I think it makes sense, right? So that's the reasonable scope for a single session. And I'm already going for third hour, but as I already said, it's probably going to be a long session, so that's totally fine. Are you using your Kimi machine? Yes, I'm using my Kimi machine. Raylib on ARM, that requires access and stuff, right? So I don't think I want to go that route on this session, right? So I need to define a good scope for this specific session. Everything else should go on separate sessions. All right, so we got this thing, and on top of that, I'm gonna put to-do in here because it's not enough to just put arguments somewhere. You also have to, you know, perform the call. Right, okay, so here's the value, and so essentially the value goes into register, right? The value just goes into that register. So it's be append, right, C, so it has to be output C, like so, and we're moving into the register a certain value, like so. So in the register is, yeah, it's registers. Oh, it's just a reg. I can just use it like that. So it's a register and the value. And so that's it. Okay. Okay. And now it fails at trying to perform the call. And to perform the call, we just do BL that function, right? So as be append, so output, it has to be C literal. So it's a C literal. BL that function, and where's the name? Yeah, so here is the name. Okay, and I think that's it, honestly. I think that's it. So that compiled, so take a look at the S. All right, so that's what we're doing here. So I put 34 in here. And the original program looks like this. So I have external exit function, and I just call it with the argument 34. It's pretty good. It's pretty good. Okay, so now let me SCP this thing, bonding. Okay. So now maybe I can actually create a separate terminal and basically switch between them. So now, like this, then compile and run it, echo 34. So yeah, we now able to compile this kind of program to ARM. And it's not that difficult, right? So it's a few ops into intermediate representation. So that's pretty cool. Absolute trading, absolute trading. So what's going to be the next thing? I suppose the next thing that we need to implement in here is hello world, right? Hello world. So that's definitely something that we need to implement. And let's actually exit with 69. So two external functions. It's kind of cool that in gas, I don't have to forward declare them. It's rather convenient, right? So I think the only platform for which I have to forward declare them is FOSM, actually, which is kind of weird, but I mean, I think in FOSM you can customize like where to get them, whether from PLT or not PLT. It's kind of bizarre. But anyway, let's try to compile this thing kind of thing, and it panics at data offset. And for the data offset, we need to use that weird syntax with loading 12 bits and shit like that. So for the offset equal to 0, I think it's kind of easy. Right, for the offset equal to 0, I think it's relatively easy because we can just copy paste that thing that we did in here. So I'm gonna go to full S. Yeah, so we can just copy paste that. It's not that difficult. But then, like, if I need to do more offsets, how do I add offset in here? So that's kind of bizarre. So I'm not sure. We can do an additional add instruction in here. So add x0, x0, and the offset. But I think like extra instruction is kind of weird. All right. So for now, the thing I want to do is maybe check if offset is equal to 0. We're gonna do that. Otherwise, it's like implement that later. So it's only we only support like offsets equal to 0. Does this P stands for soup? It stands for stack pointer, if I remember correctly. Okay, let's copy paste this kind of thing. Right, and that's the two instructions that we need in here. So let's wrap all of these instructions into string literals, like so. SB append output. So at the end, let's put new lines in here, and let's close it like that. So we might as well also put this thing. So we want to replace x0 with s because the register is going to be customizable, right? It's a customizable register and it's reg, right? Depending on the argument. And also mcg is in fact .dat. Not data, but that. And I think that's it. String literals, yeah, sure. Okay, so something didn't work out very well. This is found something. What you don't like, I don't quite get it. So yeah, there is a little bit of a problem. So this thing returns an integer, and this thing returns void. So to fix the compilation error, you have to wrap it like this. And that fixes the compilation error. Who just sick-faulted, excuse me? Who just sick-faulted? Oh, it's my compiler probably sick-faulted, okay. Oh yeah, my compiler just sick-faulted, okay, that's cool. So I wonder why though. It's kind of weird. Why did it sick-fault? Forgot S. Oh yeah, so it's actually a reg. That's right. Because it's a crust, so that's why it's sick-faulted. Borrow checker would have caught that. There we go. So this is what I'm talking about. So this is the data section. This is our data section, and we're just loading some stuff from the data section. So let's actually maybe put some more interesting messages in here. For example, hello from a arch. Hello to a arch 64 from B. Right, and then we exit with 69. So that's what we can do in here. So, and full S. Yeah. That already looks kind of cool, right? It looks legit. So, because all of the heavy lifting of compilation is already done by the compiler just generates intermediate representation, and our job is to take this intermediate representation and just like translate it to some sort of assembly, right? So, and it just like emerges, right? So a program actually emerges out of that. So let's actually try to now SCP this entire thing, bonding, right? And in here, let's do as, and then CC. So here's final foo. Hello to AR64 from B, and it exited with the code 69. So we already have a arch target, like to some extent, not everything, but to some extent. So yep, absolute shredding, absolute shredding. That's kind of cool, actually. Damn, like this streamlines adding more targets. Right, it's actually super easy to add a new target, right? Just like go ahead, take intermediate representation, just translate it to, and it's not that even difficult of a process, right? So you want to do a certain thing, you can just take the output of GCC, study it, understand what it's doing, okay, and then just use the same approach in the compiler, right? You don't even need that much documentation. Maybe you need the reference manual for the arch instructions and also reference manual for the GNU assembler, right? And it's just like a pretty routine process, right? So there should be no blockers in doing so. Just go ahead and just grind through all of that. So it's pretty cool. That's pretty cool. So what else can we do in here? Like we need to be able to also allocate, variables on the stack. So this is something that needs to be done. So I don't think it's going to change anything, right? So it will just compile and the output is not going to change. And this is because we don't really use this variable for anything. One of the things we can do in here is just like we can assign 69 in here and just pass this thing in here. So that introduces like a lot of things simultaneously. So we have a half of an hour, so I think we should be able to implement this kind of thing. By the way, let's also implement put maybe mod simpc in here, like so. Alright, so forgot the semicolon. Look at that. It actually tells me that I forgot the semicolon. That's pretty cool. Didn't even spend 3 hours debugging. So what does it say? So it failed somewhere here. So auto assign. Okay, so it tried to assign a certain variable and it kind of failed at doing that. I'm pretty sure C doesn't simp. How do you know that? All right, so auto assign. We need to do an assignment. So what kind of stuff do we have in here? We have index and an argument. Okay, that's pretty cool. So this is the index of the variable on the stack to which we're trying to assign an argument. An argument is a thing that could be also on the stack, or it could be a literal, or it could be in a data section, right? So it's one of 3 things. In the future, we're gonna have probably 4, and it's gonna be like another section with uninitialized data, right? So because when I'm allocating like vectors, right? So, and I don't initialize them, right? It's probably gonna go somewhere in BSS initialized with 0. So yeah, we need to do an assignment, but we need to know how you even assign things on the stack. That's a real question. It's an interesting question, honestly. So let's go somewhere hello.c. Let's try to learn about that. So let's do sum, right? And if I take a look at the make file, we do not optimize anything, which is good. So let's do make, and let's actually rebuild everything. So it's going to be all, and here we're building s and foo, right? Rebuild everything. Cool. Let me open hello.s. Hello.s. Here is the sum. That is very interesting prelude in here. Look at that. We subtracting. Okay. So this is how you allocate shit on the stack, right? So you just subtract some stuff from SP. But where is this prelude that we put in here? Where is this prelude? It's kind of an interesting question. So this prelude essentially, yeah, I'll need to study. So the prelude was for the main only. Yeah, it looks like it. It looks like it. It probably just stores the return address somewhere. You don't need to save x39, x30 if you don't BL. Ah, this one is interesting actually. So we can try to maybe trick it into doing so. So what if so this is sum, and let's call it sum implementation. Let's actually call it like this. Sum implementation. And here sum A and B. Return sum implementation A and B. All right. That's cool. So this is sum implementation, and in sum, it does this interesting prelude. It also does this kind of weird thing, but I mean, we can explore that a little bit later. Right, so essentially, you need to do this kind of stuff when you call to some other functions, but it's optional. But if we always do that, it's not gonna hurt, right? It's not gonna hurt. One thing I want to try to do is I want to try to see how it is to allocate some stuff on the stack plus being able to call something. Let's actually try to see that. So let's go to hello.c, like so. And how can I even implement that? So let's call it something else. Sum, and let's call print sum. So this is going to be print sum. And what we do is just something like this. Yeah. This is what I want to see. So how it is when we allocate something on the stack plus calling external functions. What exactly is going on? All right. So B, so E hello.s. All right. So print sum. Aha. 48. Look at that. Aha. So essentially, and this is really interesting, if I want to allocate something on the stack, I have to do 16 plus the amount of auto variables I'm trying to allocate in the stack multiplied by 8. So this is what I have to do. Did I understand it correctly? I think I understood it correctly, right? So there is additional space, and then you allocate some additional stuff. So it has to be 16 bytes aligned also. But I mean, variables are all 64 bits anyway, so it's going to be probably 16 bytes aligned anyway, right? So we don't have really weird size data in B. B is a very simple compiler that only works with words. So I don't think we have to worry about this kind of stuff in here. But that's okay, so this one is weird. Fuck. So you'll get bus error. Okay, so let's actually get bus error and then worry about things. So we're gonna try to do it like that. We get a bus error, we're gonna try to resolve it. All right, so does anybody know what is this exclamation mark? It kind of looks like a comment, but I don't think it's a comment. It's kind of weird thing, but anyway. Okay, so then we just move this thing. I don't think it's important. So str is kind of weird. So we do str and ldr, right, just to load this kind of stuff. So updates sp after subtracting. Updates sp after subtracting. That's really interesting. But anyway. Okay, so let's continue. So what do we need in here? str. str is kind of a weird instruction. Like, what's up with that weird instruction? str. There's no such instruction in here. Huh. Oh. Immediate and register. Alright, alright. Store. It's kind of a funny way to call a store instruction. It's like store a word or double word from register to memory. The address that is used for... Okay, so it stores the word. That is understandable. So it moves... we don't have to worry about this shit, do we? Right, store register. Right, so it takes... But what's the order? So it takes some stuff from this stack and it stores this into here, but then it uses LDR, which raises the question, what the fuck is LDR? What the fuck is LDR? Alright. Loads a word, a double word from memory and writes it to a register. So I don't understand why you have two of them. Stores a word, a double word from a register into the memory. Right, so that means, what's the order? So it stores this thing into here, then into here. Do I understand correctly? So that just... So STRs... God freaking damn it. Yeah. So, and if I understand correctly, what this thing does, it simply just loads all of these things onto the stack, right? It takes all of the arguments in the registers and puts them into the stack. Then it takes them away from the stack back into the registers, performs the add, and this is because it's not optimized. Oh, it's a swap, right? So it's kind of a swap. I see. So because it's look, why does it swap them exactly? Well, I mean, it's kind of unfair to criticize this entire thing because we compiled it without any optimizations, right? So it's just like, it's not like our compiler produces better code anyway, right? So if I enabled optimization, it's probably going to be smarter, but it's kind of funny. It swaps them around and then it adds them anyway. So swap into add. Oh shit, this is so fucking funny. Wait a second. It really is swapping arguments to fucking add them at the end. This is so... Alright, anyway. So then it adds them, right, and it saves them back onto the stack, right? And we don't do anything with them, right? We don't really do anything. Well, I mean, it loads them from the stack again, so then it can put it into printf or whatever, right? So because it then needs to call printf. It needs to call printf afterwards. That's understandable. Okay, so there's also strings and stuff like that. So there's this string. Right, so yeah, so LC. So the approach that this compiler uses for data section is that for each individual string, it allocates like a different label, right? So it has LC0, right? So then it has LC1, right? And all of that is separate. Okay, so that makes it easier. So the way I work is that I basically have one single data section and I just put everything into that data section and I just store the offsets for different string literals, which may not be a good idea, honestly. I'll probably have to refactor that a little bit later, right? So, but anyway. Oh boy, oh boy. Okay, so so here, what do we need to do? So we need to think about like what's the arguments in here, right? So what's the arguments? Because what I'm trying to store is an immediate value into a variable, and maybe this is something that I have to actually do explicitly in here. So hello.c. All right, so let's put 69 and let's do rebuild. So hello.s. So where's 69? Let's find 69. Yeah, that's a little bit annoying, right? So it doesn't tell us how to save that thing into there. Okay, so if I want to store something into the memory, right? So how would I do that? How would I do that? Okay, so I'm getting a little bit tired. I'm also getting a little bit hungry. So I think I'm gonna finish the session in here, right? And then I'll see how I'm gonna continue about it. So I'm either gonna do an offline session or I'm gonna do the second online session tomorrow. I think it's a good idea, right? So, and we already kind of established the workflow in here, right? So just like implement the operations that you need to implement, and just use the GCC as source of inspiration, right? I think it's fair. So, but the scope of the session today is going to be making the Fibonacci example work, right? So, and the final video is going to contain everything to achieve that. So let me take a look at the subs. Thank you so much to Demigods for the sub and the message. Almost forgot this month. Thank you, Mr. Zozin, for the hours on infotainment you provide. You're welcome. You're welcome. All right, so that's it for today. Thanks everyone who's watching right now. Really appreciate it. Have a good one, and I see you all on the next recreation programming session with Mr. Zozin. As usual, I love you all. Mwah. All right, this is the next day, and let's continue, right? So I decided to do that online, right? So because it's kind of fun, right? So it's kind of boring sometimes to do offline sessions, right? So along with friends in the chat, it's not that boring. It's not that boring. Admittedly, sometimes those motherfuckers being pretty annoying, but I love them anyway. I love them anyway. I love my chat, actually. I love my chat. So anyways, so let's continue. We're trying to make this specific example compile. All right, we're trying to make this example compile, and let me see if I still be able to do that. So foo.p. Well, I mean, it compiles because I actually compiled it as x86-64. I should actually put the target, which is gas arm. Gas arm. Let's go. And it panicked, and it couldn't do any freaking assignment. Couldn't do any freaking assignment, and the assignment we're trying to do in here is actually this one. It's actually this one. Let's take a look at the assembly that it generated. As far as I know, yeah, it didn't really allocate anything, right? So, and I remember that we're supposed to actually do something in here. So here's the autovar. Right, so plus 18, and yeah, it didn't. Maybe I have to revert the whole thing. No, that's kind of bizarre. Look at that. Actually bizarre. Did it get, how is that called? Optimize the way? But we don't even have optimizing compiler, so that's kind of weird. Right, so essentially I allocated one automatic variable, and I would expect, right, I would expect that to be reflected somewhere here, but it didn't get reflected. So there's something sus in here. I think we must investigate, Chad. We must investigate. So maybe what I have to do actually is recompile my entire compiler. Maybe that's the case. Right, so it still fails in here. So autovar, aha. Yeah, okay, so that kind of worked because I've removed to do in here, right? So let's bring the to do back. Okay, so it finally files in here. And if I go back into assembly, no, not that assembly, but the ARM assembly, revert the whole thing, it still doesn't do shit. Right, so let me see. Because it's 16 plus autovars count, right? It's supposed to have something at least. So let's actually do a little bit of a printf debugging. So let's fucking go. Something is fucky-wacky, chat. Something is fucky-wacky, and we must investigate. Must investigate. So let me grab this variable. Let's put it in here, and I'm going to. So this is size. It's a U size. So we're gonna put this autovar somewhere here, right? So let's actually try to do this kind of thing, and it's 2. Look at that, like it's supposed to be 2. Then here is the name, and here is LD, so it has to be 16. So did we reset this kind of thing like anywhere? I'm not quite sure. I'm not quite sure. What I'm thinking is, maybe I gotta remove this as thing because it's not getting regenerated. Okay. Aha. Ah, that explains it. Because it panics at here, obviously it doesn't get generated, and I just have a previous version, okay? We're off to a great start. Cheers, everyone. Welcome to software engineering. So yeah, anyways. I mean, if we manage to compile it successfully, it should work, right? So, but it obviously didn't. One of the things we can try to do, by the way, to make it successfully compile is comment out this thing, all right? So, and maybe comment out even this thing. So just like allocating a variable, all right? Then I go into foo as, right? I'm gonna revert this entire thing. Look at that! Look at that! Oh boy, that's a huge ass number. So like. A lot of shit allocated on the stack. A lot of shit allocated on the stack. Okay, so let's actually see what's going on here. This one is autovar. Aha, I see. So this is because it's kind of like a negative. So it expects it to be long int, which is basically signed 64, right? So, and for some freaking reason, something went wrong in here. So let's try to maybe use ZU in this specific case. And I'm gonna revert. This, what the fuck did I just open? News. There is a RSS reader in Emacs. I accidentally opened RSS reader in Emacs. I didn't fucking know it has an RSS reader. But anyway, how did that fucking happen? So that's the beauty of using Emacs. You can accidentally open some, you know, web browser or email client or some shit like that. So it's a new sticker tree view. What the fuck is a new sticker? Does anybody know? New sticker. Just a second. Emacs new sticker, and I don't remember installing it. So it's a feed reader for Emacs apparently. So yeah, the more you know. The more you know. Accidentally open the shit. This is so fucking funny. I wanted to just revert the buffer. Yeah, it still gives me a huge ass number. Why does it give me a huge ass number, even though it's not supposed to be a huge ass number? Like, what the fuck, Brevsky? Ah, this is because I put a name in here. Yeah, so I wish there was some sort of like a reporting on formatting arguments, but we're programming in Crust. So it is what it is, and it isn't what it isn't, right? So is it not? I think it is. The missile knows where it is because it knows where it isn't, right? So, and minus 32, look at that. Isn't that a poggers? Isn't that a woggers? I think that's pretty freaking poggers. So anyways, one of the things we can now do, we can now try to upload this entire thing to a Penguin, right? It's not really Penguin. Yeah, it is Penguin, right? So it's a basically virtual machine. All right, so let me grab this entire stuff. I'm gonna go in here specifically, and I'm gonna scp foo.s into root at 127.0.0.1, port big port 2. And yeah, so just like copying it into home, I suppose. Okay, this is gonna be dot. It's a bonding, right? So, and there we go. We can take a look at this entire thing. Right, so foo.s. I remember some people said that if the stack is not properly aligned by 16, right? If it's not aligned by 16, this entire thing is going to actually be bussing. So I'm gonna get the bus error. So this is precisely what I want to test right now, right? So people said that it's gonna be busting, right? So let me do the guess. Maybe I should actually create like a make file for this specific thing. So let's actually do make file. So this is gonna be foo.o, foo.s, and it's gonna be s. Well, I mean, I have to do no expand tab, right? So something like this. And so it's a so foo.o foo.s, right? So, and then here I can do something like this. So it compile it, and the final executable is going to be foo.o, and I'm going to do cc o foo.o, right? And let's try to remake this entire thing, and as you can see, it is working, and it didn't go bussin', chat. Somebody said it's going to go bussin', but it didn't go bussin'. Maybe this is because we haven't tried to read or write into the stack, right? So if we try to do that, it's gonna go bussin'. So what do you guys think? Is that true? Is it gonna be bussin'? I think it's gonna be bussin'. So it's divisible. Oh, it accidentally happens to be divisible by 16. All right. So, but I mean, is it really? So factor 32, I think. Yeah, I think it's divisible by 16. It's also divisible by 16. All right, all right, all right. I wonder how that happened. So it's just like, we only allocated like one thing in here. Or maybe we also allocated like additional variables or something like that. I don't freaking know. Anyways, so let me uncomment this entire thing, and I'm going to try to compile, and it's going to be panicking, and we need to somehow assign a variable somewhere. We need to assign a variable somewhere. Okay, so I think I want to move all of this shit to some places in programming, right? So for example, here we have a B compiler. Here we do experimentation, right? So maybe I'm gonna move hello to hello C, and I want to create a folder for which we do the output. So I'm gonna call it foo, right? So this is gonna be foo, and I'm gonna move all of this stuff. So all of the foos are gonna be moved into programming foo, right? So something like that, and also move makefile into programming a foo. Right, so this is what we got in here. So this one, here we're just like testing how the output of our compiler actually compiles on our machine, right? So as you can see, it compiles and it also prints this kind of thing. I suppose it returns the 0 exit code, which is understandable, so that's pretty cool. That is pretty cool. I wonder, by the way, can I do something like TeamUX? Yeah, so there is a way to do TeamUX. So then I can do something like foo, here's that, and I can create a separate tab, right? So as you can see, there are 2 tabs in here, right? So one for experimentation, another one for actual testing. And here's the hello.c, and this is where we're gonna be doing different stuff, right? So let me open hello.c. So the thing I wanna be able to do is essentially, I want to be able to allocate some shit, right? So let's remove all of that stuff. We got some subs, by the way, so should I acknowledge the sub? I think I want to acknowledge the subs. So who should I start acknowledging? So there is quite a few people. So 7 months ago, well, I mean, so 23 minutes. So thank you so much. The weird nickname, I think I already acknowledged you. DW Silos, thank you so much for your one with the message. Why is Suwon not in the reverse anymore? Oh, you mean, so at the beginning usually, or on the breaks, I run this entire thing and it basically counts up, right? And I usually have a limited amount of like time for how long I wait, like 10 minutes or 5 minutes. And instead of counting down, it counts up. So I count up so you know like how much overtime I am, because I may go to the kitchen and cook, like not cook, but brew some tea, but it may take longer than 5 minutes, right? So sometimes that happens, and I want you to have that information, right? Counting up and then saying on the screen, like making tea for 5 minutes, and you see that it's actually 6 minutes. You know that I'm actually 1 minute over time, so it gives you additional information. So no negative, I think it doesn't support negative numbers, right? So I don't remember how it's, and honestly, negative numbers are kind of difficult to read in that regard, right? It's just like, it kind of looks weird. Right, when you see that I'm supposed to actually come back in 5 minutes, but it's already 6, it's kind of obvious that it is over time. When it's negative, like some people may even miss this negative number. I think it's more clear. But anyways, so yeah, Dance, thank you so much for the spine. Thank you. All right, so anyway, let's try to allocate some variable in here, right? So, and I'm gonna try to assign this entire thing. Like so. So let me open makefile. Here we're building only the assembly, which is understandable. So here's that, and I'm gonna try to build everything. So we're rebuilding everything. Okay. Hello.s. Let's open that, and here is the main, right? So we just subtract sp. And if you want to just, that's very interesting, right? So if you want to just allocate something on the stack, you can just quickly do this kind of thing. But I mean, yeah, so you need to do all of that weird shit if you want to be calling different functions, right? So that's totally understandable. And then the way we do that, right? So I think I already kind of remember, is that we have to first move the number that we want to save onto the stack into a register, right? So because then we're storing the register into the memory. So then we move in 0, and that's additional stuff. I suppose this is the return value of something. All right, so anyway, I think now I understand what we need to do in here. Right, so let's go into the panic mode. And within the panic mode, I'm actually curious, what is the argument, right? So we can have several arguments in here. So the enumeration, arg, which argument exactly failing in here? I suspect this is going to be a literal, literal. So let's actually put stuff like that. And this is going to be underscore, this is to do a boom. All right, so what do we have? panics at literal, and here is the value of that specific literal. So, and essentially what we want to do SB append into the output, and what we're appending in here is essentially move x0 and that specific value, right? So and that value is basically here, right? So we're first moving this entire thing into LD, and I suspect we're gonna actually add more things in here, right? So we're gonna have more things in here. Okay, so then after that, we have to move that into SP12. Which is rather interesting. Why exactly 12? 12 bytes. That's a really specific, very specific value, honestly. I wonder if I actually say that this thing is not really an integer, but something like uint64t. How about that, right? So it's exactly 64 bits. So it's probably not going to compile because you have to import int thingy, right? So let's actually do this kind of thing. So stdint, and let's do something like that. So that seems to be working. And I'm going to open hello.s, right? So what do we have in here? Okay, that at least makes sense, right? So here sp, and we store that x. Okay. So that explains it into sp8. Right, so that is already something that I can comprehend. So that means SB append output, right? So, and we're storing x0 into SP, but subtract it with like ZU value, right? So actually edit, right? So because it goes that, and we have to, I don't remember, does it subtract or does it edit? I suppose maybe that's basically subtracting. But anyway, so this is basically, yeah, this is the index, so we do index multiplied by 8. And do we always, yeah, so it's basically index multiplied by 8. I think that's what we need to do in here. I think that's basically what we need to do in here. So, all right, anyway, let me see. So this is not C or something like that. So let's fucking go. Let's freaking go. All right, so it compiled, as far as you can see, right? So it compiled, and we can take a look at the final thing that we got in here, right? So this is the final thing that we got in here. So this is that, and yeah, so we subtracted the stack and so on and so forth. Yeah, so we saved that and we put that onto the stack. Put that onto the stack. So that seems to be fine. So the thing I want to test now is that I want to test if it's not going to be busing, right? So that's one important thing that we need to check, whether it's busing or not. So let's actually go in here, and I'm going to just like copy paste this thing in here, bonding, right? We'll put bonding in here, and let me cut the whole thing. So here is, do I have a saving? I don't see. This is because I'm actually saving at home, right? So here is where it is locating, right? So I actually moved all of that stuff to a different place. So what is it called? It's called foo. So what I have to do now, right? So instead of that, I have to do something like programming foo. This is where we're gonna put all of that stuff, bonding. All right. So, and now if I do cut.s, so here it is. Here we're saving all of that into like 69 and whatnot. Right, so, and then I'm gonna try to build the entire thing. Right, okay, so is it bussing? It's a little bit bussing. Look at that. It is in fact a little bit bussing. Bussing around. All right, so let's actually comment out this specific thing and see if that's what's bussing in here. So I suspect it is. I suspect that's what bussing. All right, so let me see. All right, and then if I try to run this entire thing, it's not bussing. Okay, so let's see what exactly is wrong in here. What exactly is wrong in here? So it's supposed to be divisible like by 16. And I do not quite understand. It's only bussing when it's busser. It's merely segmentation faulting. Okay. Like, I'm surprised that this is that, because what I'm essentially doing, I need to kind of draw it out, chat. I need to kind of draw it out to find out. So this is what we have in here. Right, and this is basically SP. So let's just assume that this is SP. And let's assume that maybe 4 dots in here is a single word, which is 8, which is kind of confusing, but that's fine. Right, so, and essentially I subtract this thing, and then, for fuck's sake, okay, 1, 2, 3, 4. Right, so might as well do things like this. Right, so maybe like this to sort of like separate each individual word. Each individual word in here is, you know, 8 bytes, which is kind of, well, I mean, I'm not sure if it's going to be super confusing, but that's basically what it is. Right, and in here, we just allocated this kind of thing, this much, right? So we allocated this much. And as people said, it has to be divisible by 16, right? It has to be divisible by 16. So that means the 16 boundaries are going to be like this, right? So the 16 boundaries are sort of like this. Do I understand this correctly, backseaters? Do I understand this correctly? So this is basically the 16 boundaries. This is basically 8 boundaries, but we have like 8 boundaries. Okay, and when I do this kind of thing, SP, yeah, this is not what I want to be doing. Like I need so the usual way I do that, is essentially, what is it called? From a base pointer. Right, so I'm not doing that from a stack pointer, so I already see the mistake. I do that from a base pointer. I need to somehow find the base pointer in here. So, which is a really interesting question. Like, is that a common thing in ARM? Is that a common thing in ARM to have a base stack? 16 is a weird alignment to inform. Like, this is not helpful message. Right. So let me see. ARM. So stack base. Right. Is there sort of like a stack base in here? Where is the base in empty, like a stack base, like ARM RBP? So I want to like an analog of RBP. So X12 can be, oh, this is actually a good point. Oh, we're saving, yeah, that's right. That's actually right. So we're using, okay, so this is where we're saving this entire thing. So this is a stack point. All right. Funnily enough. So how do we do all of that? X12, but the speed doesn't change either, so doesn't matter. Does it change or does it not change? Ooh, I'm not quite sure. To know whether it changes or not, well, yeah, it doesn't change because we just allocated it once, so we can kind of do that. All right, let me take a look at what we have in here. So I'm actually kind of surprised that like why there's 2 pointers in here at all. Like where do we allocating additional pointers? Ah, we're allocating it for printf, so that's why. So that explains, because printf returns a value and it automatically saves that value somewhere. So yeah, so when I do printf, does it actually? That is surprising. So the function call, I just realized that the function call does not implement storing the return value back. So this is something that we'll have to implement, by the way. This is something that we have to implement. Where is the function call? Add 8 to blah, blah, blah. Yeah, so it literally doesn't do that. It literally doesn't do that. And so let's actually put it to do. All right. So let me close the chat. It doesn't say anything related to what I'm doing. So save the result of the function call, right, to the autovar, All right, and here is an interesting thing. So I should be able to maybe remove this thing, and effectively it will allocate only one variable, right? Effectively it will allocate only one variable, so that's fine. So f.b, so this is s. Let's actually redo that, and it's now 24, right? So it is in fact now 24, and it's not particularly correct, right? So because it's supposed to be kind of Yeah, I don't really know why. I feel like chat is actually debating me on that one. I think the chat is actually debating me. It doesn't really have to be 16, but I mean, like, I just have to test everything myself. I'm gonna catch like that thing myself. All right, so what we need to do. So if we're gonna assume, right, if we're gonna assume that SP doesn't change, we just pre-allocate it once and we're gonna be computing everything relative to SP, we can try to do that. Sure, we can try to do that. So we know how many autovars we have in here, and we can basically compute this kind of stuff relative to that. We can compute all of that stuff relative to that. So here is an assignment, and how do we do that? So we just do plus. So this is going to be 4, and I can basically copy paste this thing a couple of times. In terms of SP, we're here. And so the index, right, the index is going to be multiplied by 8, right? So this is basically multiplied by 8. And it basically adds something. So at some point it could be 0 or it could be something else, and it's going to be just adding this stuff accordingly. So we're kind of doing like indexing the automatic variables from a different side than x86-64, right? So in x86-64 we indexing them from right side. In ARM, since SP is sort of like stable thing, we're indexing it from left side. Okay, so let me actually try to recompile this entire thing and let's take a look at the assembler. Okay, so I'm not really sure why it is 8. I would expect it to be 0, honestly, right? So because it's supposed to be like an index 0. This is because we're indexing them from 1. Okay, so that means I have to do something like that, right? So I have to do something like that. Okay, cool. So now if I go to f.s, all right, so that is 0, and it's trying to like do this thing relative to that. Okay, cool. Finally, so when I do x29, right, so where does it save the return address? Right, if we are somewhere here, right, so something like this, 1, 2, 3, and 24 is basically 3. So this instruction will effectively move, like this one, will effectively move this thing to here. Let's ignore alignment, and only then it will store the return address into this one. Right, it will store the return. So this is where we store the return address, and this is the rest of the variables that we allocated. Do I understand this shit correctly? So the return address stays here, right? So this is the return address, right here at the top of this thing. And then this is the rest of the memory that was sort of allocated for our needs. Do I understand this correctly? Chat? Did everyone already leave because it's so fucking boring? I feel like this is so fucking boring, everyone already left. So, or maybe nobody fucking understands what I'm talking about because this is not CSS or PHP. That's not debriefing, since it doesn't fucking matter, that doesn't answer my question. I didn't understand it, sorry, I don't know the context, it's well confusing. Okay, I see. All right, interesting. So, and interesting is that here, this is an additional sort of like a 16 thing. That we sort of like assigned in here. Additional 16 thing. So I suppose one of the things I want to do in here, effectively, is that are all of the reads have to be like 16 aligned? That's kind of weird. Are all of them have to be 16 aligned? All right, so like I'm gonna try to do this kind of thing and see if it's going to work. Okay, so this is what we managed to do. So that means, by the way, we have to not do -1, right? So we have to not do -1 because we want to skip that return anyway. Right, so we need to skip that return anyway. You can add an extra. This has nothing to do with what I'm doing right now. Don't please distract me with random facts that have nothing to do with what I'm doing right now, right here. I'm not interested in that. Right, because that's distracting a lot. Like, I'm focusing on one single thing right now. Not, oh, you know, by the way, you can do that different, but I don't care. We can discuss that later. So right now, I'm trying to just save the variable somewhere, like in the sense that is going to work. Right, so somehow, doesn't fucking matter how. Okay, so let me see. So I'm gonna revert this kind of thing. All right. So hopefully, so this is gonna be busing, right? So this is definitely gonna be busing. And so let me try to do this thing one more time. So this is going to be bonding, right? So I'm going to not save that. Let's open it one more time. All right, so let's try to build this entire thing. Let's try to build, and I'm going to just do foo, segmentation fault. Okay, so that's fine. That is totally fine. So I'm not sure the alignment. Is the alignment has to be just the size of the stack has to align, or all of the reads and writes have to be aligned by 16, even though they are all 64, like arm read write alignments. So, and none of this website are going to be open for me. Data alignment on ARM processors. So, like, I need to read about this kind of thing. So, gamedev.net, and it's probably it's open. Look at that. On our processor, the alignment of... Oh my god, stop fucking jumping around! The alignment is important and can read and write much faster at alignment position, so 2 bytes should be on even addresses, 4 bytes long should be on addresses divisible by 4, and the code's alignment, the... Fuck you. Take advantage of ARM. This is not about taking advantage of the ARM alignment. So only SP needs to be divisible by 16. That is a weird requirement, but then within starting from SP, I can do unaligned reads and writes within SP. So it's just like SP, the value of SP itself has to be aligned by 16. So, maybe stupid, but if the stack is aligned by 16, all reads and writes of 64 bytes, you mean bits? That is kind of... The fact that it has to be like that is kind of stupid. Like, this is bizarre. Like, why? Anyway. Okay, so how can we easily like align this kind of thing by 16? So essentially I have something like this. Right, and it's not divisible by 16, right? So there should be something like align bytes, right? So align bytes by 16. So that's basically what we're trying to do. And this is going to be a function, unsafe function, which is public. So yeah, this is going to be... So this is the bytes, and this is use size, and this is alignment, also use size, and this is what we want to do in here. And the annoying thing is that I have to solely rely on the chat about this kind of information, and all of the stuff on the internet is bullshit. So it's like, right, it's just like, it's very annoying, right? So, and LLMs fucking lie, so you also can't actually be sure 100%, so it's very annoying. All of this shit is very annoying, but anyway. Okay, so how do I align things? I don't quite remember. So if, like, it has to be divisible by alignment, right? It has to be divisible by alignment. I remember there was a cool way to do that. But I kind of forgot how to do this. So if you have some stuff, for example, something like this, right? So you have 4. And it's already kind of divisible by 4, right? So it's divisible by 4, so you don't really have to do anything. But if you have something like this, you may want to add something. So usually you can figure out this part by doing mod, right? So if you do bytes mod alignment, right? So this is alignment, you get this part. Then quite easily, you can subtract that part, and this is how much you have to add in here, right? This is basically how much you have to add to sort of align it properly. So then you take the bytes, right, and you basically return this entire thing. So is that a good way to align things? Probably not the fastest one, because I remember there was like a smart-ass way to do that with bit shifts, because it's supposedly faster or some shit like that. Right, so if it's already aligned, right, this is going to be 0. So effectively, it will add additional thing in here, which is, does it really have to be, do we have to add this entire stuff? Right, so maybe one thing we have to do, if bytes add, well, so we can do something like a remainder, right? So we can save this as a remainder, and if remainder is greater than 0, we do that, otherwise we just return bytes. So that's one way to do that. Right, so just going off of the, yeah, so there is some sort of a smart-ass way to do that, like I don't want to think about it. Okay, so yeah. So we're not going to be doing the smart-ass way. All right, so we kind of align this thing, and I'm pretty sure the compiler will optimize it properly, or maybe do something, some magic or whatever. Who cares? Okay, so let's do this kind of thing. Yeah, so this is 16. What if I create another variable b? Right, so we're going to do this kind of thing, and well, that's understandable. That's actually understandable, so because you can actually fit 2 of them. But we also need additional variable for the return address. So this is very important. And this is something that I forgot. So additional, so vars count +1 for the return address, right? So +1 for the return address. And this one may actually produce something interesting, right? So it's 32 now, right? It was basically 16 before, but then it was 32. So, and now if I go to foo b, I remove one variable, right? So that means it's only a and return address, so it's gonna drop from 32 to 16, right? So this is basically what it's going to do. I'm going to revert this entire thing, and now it is in fact 16. Okay. Oh boy. So everything seems to be aligned. So everything's fine, more or less. Okay. So let me try to copy this entire thing. Bonding. James bonding, and so let's do something like this. All right. So I'm going to rebuild this entire thing. It is still bossing. All right, let's troubleshoot, chat. Let's freaking troubleshoot. So what's up with all of this? So is this something? Just realized that we have to be careful with this kind of thing. GDB time, I'm not really sure. So why are you still obsessed with alignment? We already passed alignment a long time ago, chat. Jesus fucking Christ. All right, so where can it basically fail in here, and why? That's an interesting question, isn't it? Right, I suppose it may be failing only here, right? So it may be failing only here. Right, so and then if I try to do that, right. So SP8 storing 30, which is needed by our ARM. Where is it storing? Well, so what? We're not storing anything. We're not, like, who cares? I don't get it. Where's the problem? Anyway, whatever. Okay, so is it busing? It's not busing, right? So, we are storing the return address at the top of the stack, right? At the top of the stack. My guess is alignment down and not up, whatever. So x0. Why this doesn't work? Right, because according to my understanding, right, so this is what we have. This is the first word, 1, 2, 3. So SP, right. We basically modified it, like we put it in here, right, by doing this kind of thing, Then, by doing this kind of thing, we stored in here a return address. Okay, cool. And then by doing SP8, we actually stored X0 in here. So this is where we stored 69. Where is the problem? Where is the problem in here? So when you store to SP, you are writing to the space where X, but isn't X29 is stored in here? You storing two registers. Wait, STP stores both X28 and X30 in these two spaces. Wait, STP. So what STP does? Store. Holy shit! I thought maybe it just stores and just like does additional thing with X30. Okay. So essentially we have to allocate two additional things where we're gonna store both X29 and X30. Right, and this is where, and one of them stores the return address or whatever the bullshit it is, and only then 69. Okay, I mean, sure. What that means, so let me take a look at the STP, right? So let me take a look at the STP. So where was the ARM? So register instruction, is that where it is? Yeah. So will I be able to find STP in here? STP store pair, register to pair, register calculates address for base register value and immediate offset and stores two 32-bit words or two 64-bit double words to the. Okay, understandable. So now it makes sense. I think I finally figured it out. So we're gonna figure it out. I promise we're gonna figure it out. So that means it has to be 2. Okay. So because additional X29 and X30, we're saving it and also automatically modifying it. So, but then what the fuck is that? We're saving SP into X29, right? So what does move do? Does it save SP into X29 or X29 into SP? So which one it saves where? So which order, right? Because some of them X21 is like RBP, that doesn't answer my question. X29 to SP or SP to X29, who saves it where? SP to, okay, so SP to X29. All right. So X29 becomes a base pointer and bro, this is madness, honestly. Anyways, so we'll also align it B16, whatever, and so that also means that we have to do +1, right? So because we have to, index is already starting from 1, and we have to just like save it in there, right? So we have to save it in there. So and this is +1, and this is where we're gonna be putting it. Okay, so hopefully that will work, right? So. Okay, so foo.s, and let me take a look at what we have. Right. Okay, so that's fine. That's totally fine. We're allocating basically 4 words in here for X29, X30, and 1 for the temporary variable that we have, plus additional one to align it to 16, right? And this is where we're saving all of that. We're saving that to X69. Okay, let's fucking go. Hopefully that is how it works. So let me actually close this thing. Do not write anything in here. So one more time, bonding code foo.s. Everything seems to be correct. So make B. It's not busting. Holy shit. Okay, let's go. So what's the next thing? What we're gonna be doing? We want to now, since we save it into that temporary variable, we want to pass it to exit. So let's see how it's going to go. I'm going to try to recompile it, and it's panicking. It's panicking in here because it's trying to read that from that weird place. So it's an index, and it's kind of similar to all of that shit, right? So we're moving into the register, but we're moving the, I suppose, SP ZU, and that ZU is this formula. So that's how it's going to be working, right? So if we did everything correctly, okay, let's go. Okay, so let's take a look at this thing. All right, look at that. So we're saving this to 69, then we're storing that thing into here, then we're moving it back into X0. Again, we're not optimizing anything, that's why it's so weird. When you disable optimization for GCC, it also outputs weird as code, so that's totally fine. And then it calls to BL exit, right? So it calls BL exit, and I suppose that it's going to exit, and it's going to exit with 69, hopefully. All right, let's fucking go. So I'm going to copy this thing, bonding, James bonding. Let's take a look at what we have in here. So this is that. I'm going to try to rebuild this thing. Fuck you, Letterman. Fuck you. So what exactly did it do wrong? So apparently you can't do this shit with move. Do you have to do store? I think you have to do store, don't you? Or, oh, it's actually LDR. Yeah. So you have to do LDR if you want to do this kind of thing. Okay. So an LDR is going to, you know, do that fully. It's kind of an opposite operation in here. Right, let's try to do LDR. All right, so now I'm going to do bonding, and let me take a look at this kind of thing. Is it bonding? Is it bonding? It is James bonding, and a boom, echo, absolute fucking charging. Fuck you. Absolute fucking shooting, chat. We did it. We fucking did it. Thank you so much, everyone. Thank you so much. Like, I don't think I will be able to do that as quickly as we did it without your help. So, yeah. That's pretty cool. So I think I'm starting to understand how this entire thing works. There's too many weird details, right? That's, like, you don't understand why it is like that, but like you have to do these bureaucratic rituals, right? So ARM so far feels very bureaucratic for some reason. It feels more bureaucratic than x86-64, honestly. What do you guys think? BL always like branch, if less, to me, so confusing. Well, I mean, yeah. So gotta add, yeah, that's true. That is actually true. Just a second. So we don't really do that. Yeah, we actually put 16 in here. So maybe we can put something like this, like a stack size. All right, so stack size. This is stack size. And then down there, this is ZU stack size. Yeah, that is true. Thank you so much. Fuck you, Letterman. So full S. Yeah, there we go. So it's a 13, and we're aligning everything properly. Damn. Sorry. Now, let's try to actually enable all of that simultaneously. We're gonna put, so D, maybe LD in here, and we're gonna try to pass A in here, and we're also gonna try to exit with A. Right, so that's what we're doing in here. This is not what I wanted. Foo.s. All right, so we're trying to call printf with also the same thing. So we're saving 69 into that temporary variable, right? Then we're initializing. Here is the string literal, here is the second variable, and then we do printf, and then we exit with the same sort of thing in here. Right. So let's actually see how it's gonna go. Let's do SP bonding and code fs. Let's rebuild. Hello to arch69, right? And it exited with 69. So the language slowly becomes more and more powerful. We have more and more different components in here. And this is very fucking important. This is very fucking important. Anyways, so what else do we have in here for the Fibonacci example? So the Fibonacci example does a lot of different things. Like for example, we need to be able to do comparison, right? So comparison operation. Or maybe also plus operation. Let's actually implement the plus operation. And the plus operation has to happen on the what is it called? On variables and stuff like that. So that's what we need. Okay, so we may allocate A and B. So 34, 35. Let's actually do 34. So I want it to be different from 69, so I know something changed in here. Let's also allocate C, maybe like 33. I wanted them to be different. Then I'm going to say A plus B, right? And I'm going to try to put C in here and put C in here, right? So for now, that should compile. So this is going to compile. So that's, well, it didn't compile. Look at that. Oh, because when you're assigning variable into variable, this is where it fails. You can't easily assign variable into variable. Do I want to implement it right now? I'm not sure if I want to implement it right now, but maybe I should. But anyway, so where's my example? Foo.b. Yeah, let's actually do something like this. Let's focus on what needs to be implemented in here. So, and what needs to be implemented? Binary operation. Okay, so we're about to implement a binary operation. What kind of binary operations do we have in here? So this is all of the things, right? These are all of the things. So this is a binop, and this is the index, left-hand side, right-hand side. And let's put this stuff in here. And for different binops, we're going to be implementing things differently. So binop. And what kind of binop do we have? So binop, plus, minus, and so on and so forth. All right, so let's put the stuff in here. Binop, like so, to do boom. Might as well align everything like that. Okay. So it panicked at plus. That's pretty cool. So we're trying to do plus operation. So the question is, how do you even do plus operation? So let's go. So here is experimentation situation. So I think it's something like hello. This is the place where we experiment with things. And I want to do 64A. It's going to be 34 and B. And yeah. Maybe I'm gonna like literally try to do it. It's kind of easy. It feels a little bit of too much cheating, but I think that's the easiest way to kind of learn this entire thing is to replicate it in C. A34, 35 is gonna be B, and then C equal to A plus B. So literally the same program, but in C, what exactly does it generate there? Let's see. So I'm gonna open hello.s. Right, and okay, so we're just storing things. It kind of stores as similar how we do that. Then we load in all of that stuff, and okay, so this is kind of cool, right? So we're just loading them into registers, like all of these things, we're loading them into registers, and then adding them. And I suppose this is basically the left-hand side, right-hand side, and the target, right? So I want to actually open like the add instruction. So where's the add instruction? There's no add instruction, Brovsky. Ooh, oh, it's this one. So extended registers or something like that, right? So add WWSP. I don't know. So I suppose it's a registers, right? So adds a register value and assigned or zero extended register value for, but an optional left shift. Yeah, so this is not particularly useful because I don't understand what these things mean. So it's basically a register, XD, so stop jumping, but maybe it's useful there. Is this 69? Okay, so, but what is this? Is that whose destination, who's the operand? It's kind of difficult to see it, like it's not possible to see. But anyway, whatever. We're gonna just assume things. So, and left-hand side. So we need to load the left-hand side somewhere. XD destination. Cool, but where does it say that? So, oh, D stands for destination. Jesus Christ. Okay. So match LHS. So let's do LHS. All right. Well, I mean, I understand that. This is very easy to guess. it's like the most obvious thing that you can guess about this operation. But I don't want to guess. I want documentation to explicitly tell me, like, why documentation can't just, like, have this one line in it and just shut up? Like, I would be actually super grateful. Like, what the fuck is all of this shit? It's just like, okay. Well, I mean, it kind of... So... So, like, why is it not just that? So that's my question, right? So I can guess it myself, sure, but I want some sort of a confirmation. I want some sort of a confirmation, and of course I'm not gonna get it. Gatekeeping, yeah, classic. Freaking classic. Anyways, so arg, so enum arg, so we're gonna put this stuff in here, and let's actually see where exactly it is going to crash, right? So I suppose since we're reading the autovar, all right, it's not going to... It's going to crash at autovar. So we get that. So to do something like this, and it's going to be align like this. And let's fucking go. So what does it say? I suppose we have to put semicolon here. Unreachable expression. So, well, I mean, who gives a shit? Panic. Okay. So it panics at here. So this is an autovar, and this is basically index. And in here, what we want to do, we want to move it into SP. Where is that thing we did in here? So this is what I want in here. Actually, believe it or not. So this is what I want, and I want to put this in here. So in the register in here, by the way, X is X0. So we don't need any register. So we're loading the automatic variable into the register, which is understandable. And I suppose we also need to do the same thing for RHS. We're doing that stuff for RHS as well. So this is RHS, and yeah, that's pretty much the same. And then, so the operation here is plus, right? It is in fact plus, and that just means that we have to do just add, and we have to store it back, right? So we have to store it back, and we store it in here, right? So this one actually has to be x1. Okay, so SB append output, something like that, add x0, x1, x0, like so. So we added that, and we have to store that thing back. So str, we can put that stuff in here. So this is str, but now it's the index of that thing. It's the index of that thing. And I think that's it. Right, actually, I think that is it. That is everything we need to do in here. And it panicked where? Oh, now it tried to assign something, right? It's tried to assign something, but then it failed. So this is index, but this is a sort of like a source index. So you know what I'm thinking? We can actually move this thing outside in here, because this is where we're assigning, and depending on whether it's a literal or not literal, we're going to be doing LDR differently. Where is LDR? So this is our LDR, and this is x0. So this is the index that we are loading, and this is the literal that we're loading, and then we're storing it back. I think I'm getting a hang of it, chat. I think I'm getting a hang of it. So let's actually try to recompile this entire thing, and it is recompiling. Let's take a look at l'assembly. So does it look epic? Does it look epic? So we are assigning 34 to one variable, 33 to another variable. Then we're loading up both of the variables. We're adding them together and then saving it back, right, into 40. That's look at that. Into 40. Is this one divisible by 16? So it's actually 48 mod 16. It is in fact divisible, so that's pretty cool. Right, so we're saving it back. Then we're loading this thing and we're storing it to a different variable. Then we do printf and so on and so forth. Okay, so that's pretty funny. That's pretty funny. Okay, so that looks like a code, like an ARM assembly. It's a pretty shitty one, right? So, but we're not optimizing anything, right? So that's the reason why it's so shitty, because it's not optimizing a shit. Okay, so let me close that. So bonding, James bonding, foo.s, Here is our James Bonding situation. Okay, let's try to rebuild this entire thing. It built. So what do we expect from this program, by the way? What do we even expect? So 67, right? So we expect 67 in here and 67 as a return, right? So 34, 33, 67, and there we go. So that's what we expect. And that's a lot of, like, that's a lot of functionality in here. Compiler is better at writing assembly than human when they see this. Well, I mean, it's not optimizing, right? So anyways, so let's actually try to do this. 67, just a second, hold your settings, 67, absolute fucking sharding. Chat, spam, absolute sharding. There you go, we did it. We have plus operation, we have assignment, we have almost everything to do Le Fibonacci. We have almost everything to do that. So I think the only two things are left for Le Fibonacci is comparison, less comparison, and you know, while loops and stuff like that. Where is where is OBS? Just a second. Are we live or not live? I'm not quite sure. Wait. I can't find OBS window. Where the fuck is it? I don't see it. OBS bug, bit laggy. Okay, so grab OBS, click on the tray. I clicked already on the tray, so... Oh. Like, I know how to use computers. I know how to... Trust me, okay? I know how to use computers. I've been using them for more than 20 years. So anyways, I think I need to make a small break, chat. I think I need to make a professional software audio. Exactly. I need to make a small break. I need to make a cup of tea because I'm already streaming for more than an hour. So I think the time has come. So if I take a look at the examples, right? So here's Le Fibonacci. We need this thing, and we need while loops. For while loops, we'll need conditional and unconditional jumps. So that's what we'll need. We know how to do that. We know how to do that. Literally, comparison and just jumps around. So this is the only thing. Like it's basically three different ops. As soon as we can do that, this example should work on ARM. What optimization could be done in groups, and that's it. Well, I mean, it depends on the situation. So we're gonna do optimization separately at some point, maybe. We'll see. So let's make some work. We are back. So let's actually start with comparison. We need to compare a variable to a huge value. That's what we need to do. So, and I wonder how effectively we can do that. That's a very interesting question. So I'm going to go into foob. So, and in here, I think I'm going to just like allocate two variables, right? So A and C, and here is going to be A less than 1 million. Right, something like that. So, and let's see how it's going to fail, like where it is going to fail. Okay, so we're trying to implement, we're trying to load a literal into the right-hand side. Okay, so this is the value, and the loading literal is actually kind of easy. So we might as well just copy-paste this kind of stuff in here, right? So this is x1, and we're just loading it in here, and we can implement that for left-hand side as well, because why not? Right, so right-hand side, left-hand side doesn't really matter. It's very easy to do. So, and this is x0. The only difference is just like the register into which we're not working with data of sets yet, but maybe at some point we will. All right, so what else do you want? And now binom comparison, right? So we have x1 and x0. How the fuck do I compare them and store the result back into this thing? So what is the CMP equivalent in ARM? I don't know. Let's find out. So let's go into hello, let's see. And in here, we can do a kind of a similar thing, right? So we can do a less than 1 million, right? So what is exactly it is going to do? Terminal make minus b. All right. So, and let's close this entire thing. And what is it called? Hello.s, right? So hello.s. Move. What the fuck is this shit? So it can. Oh my god. So you telling me you can't really just save 1 million into register immediately because it probably doesn't fit into like a command into operand or something like that. Fuck. Can only move 16 bits, yeah. That is painful, my friend. That is painful. So we probably want to start maybe with... Yeah, so simple things are probably simple, but this one is going to be pain in the ass. So let's go back into Hello C. So how about... So if I just do this kind of thing. So 34 is fine. Make minus b. Alright, and then I open hello.s. So here we just save 34. That's understandable. That's cool and all. So go back to C, and I'm trying to save now 1 million. What does it take to save 1 million in here? Open hello.s. Yep. That's what's going on in here. So effectively, we also... Yeah, so we just move something up until here, which is kind of an interesting value. People say it's 16-bit, but let me see. 2 to the power of 16. Why did I do that? 2 to the power of 16 is actually 15, 14. This is a bizarre thing. So it's only 14 bytes and not even 14 bytes. Yeah. What exactly going on? What is this exact value? We probably want to take a look at that in a binary form. Right. So then we move in, and also this is some sort of a shift or whatever, right? That number needs 15 bits. I see. The number needs 15 bits. That's for sure. So I understand move. I understand what move is doing. So we need to now learn move k. So what exactly move k is doing? That's a good question. Man, ARM is more anal than x86-64, honestly. How come? So move wide with keep moves an optional shifted 16-bit immediate value into the register, keeping other bits unchanged. LSL is shorthand for ls-l. So we are moving like 15 in here and moving by 16. Okay, so can I do something like 16? Right, and this is probably not what you want to do. So moves an optionally shifted 16-bit immediate value into a register. What if... So this is too much, by the way, I think. Yeah, what if I move it by 15? I don't understand what this thing is doing, honestly. So what the fuck am I even looking at? So, okay. Is the 32-bit name of a general purpose destination register encoded NRD? Okay. 16-bit unsigned immediate in a range of 065 encoded in immediate 16-bit. Okay, so that's understandable. Right, so this is the destination, general purpose destination register, and this is immediate value. Right, so shift for the next one is a shift, right? So the last one here is a shift. And this one is kind of optional and we don't even use it in here, so it's LSL16. So for the 32-bit mode, maybe this is 64-bit. right? Because this is x, so 64. It's the amount of by which to shift the immediate left, either 0. So essentially we have 0x and we're moving it to the left by 16. So that's basically what we got. And I assume that after that, what do we have to even do in here? Do we have to add this value? Do we have to add this value? Or do we have to... Oh, we have to add it. So I see. Move... Well, I mean, it's not that different from OR in it. Adding is not that different from OR in it, because here, right, so here we're gonna have a part. Yeah, I see. So how many zeros do we have in here? How many zeros do we have in here? Right, it's like literally 16 zeros, right? So yeah, okay, I see what's going on. Okay, I see what's going on. So you have some stuff like that, and you basically split it into two parts. What is that? Essentially, right, we have to take 1 million, right? So here's 1 million, and let's take a look at the binary representation of this entire thing. So essentially, we kind of split it into two parts, right? So we, through move k, we construct a value that looks more like this. That looks like this, right? So this is the value that we construct through move k, because we take this thing and we shift it to the left by 16, and that's our value. And then we basically take this smallest value in here, right? Take this smallest value in here, which is exactly that. That's what we do. So if the value is too big, we literally split it in two, right? But why? Because the instructions in ARM have a limited amount of size. They have the same size. So that means you can only move so much into the register without exceeding the size of the instruction. So it's not like x86-64 where each instruction has like a variable size, and you can like put like whatever stuff you want in here. You can only, like, you have some data to encode the instruction plus encode the register, destination register, and you have a little bit of a bits left to encode the number that you want to move in there. And if you exceed that, you literally can't move that, and million exceeds that. So what we do, we split this number in two, and we construct it back through two operations. That's what's going on in here. So yeah, that's literally what we have to do in here. That's literally what we have to do. So the register address bus says, Nuffly, yo, haven't seen you in a while. So did I actually summon you through ARM assembly? Right, so because you're into this kind of shit. Yeah, so it's so cool actually. It's kind of cool that I managed to understand like how exactly this entire thing works. Right, so but at the same time, it's too much time to implement. Is there any easier way to implement this kind of thing? Right, because now I need to think how I'm gonna split in all of that stuff and everything. So it's exactly right. You have 16 bytes. And I suppose the value, we can actually try to trigger this entire thing, right? So let's try to trigger this entire stuff. So initially, if you just use 34 and just compile it like this, and open foo.s, this is not what I want to open. I want to open hello.s. What it does, it just moves 34. Now, so you only have 16 bits to store. So what if I have something like 16? Okay, so this is not going to work, and I probably have to, yeah, so this already by itself, if you take a length of this thing, subtract 2, this is already 17. This is already 17 because this is extra 1 in here. So we have to probably do something like -1. Right, so this is -1. And in terms of that, this is the value that we have in here. So what I want to test now is, I might as well just like construct that in C directly. Main.c, it's hello.c. So it's 2, 16, minus 1. It's actually not like this, but more like this, right? And go to hello.s. It just moves that thing there. It just moves, like, because it fully fits there. Fully fits. Now, hello.c. I'm gonna remove that minus one, that single minus one, just a single minus one, make minus b, okay, open hello.s, and it's already, wait. The shift can be only 0.60, fuck! How does that even work then? So, and what is, how? So does it literally save an incorrect value then? What the fuck is this shit, excuse me? But it's more than 16. God damn it, I thought I was beginning to follow. But I mean, it's just the compiler that decided to do that. We can always just split it by 16. Look at the documentation of move. So it basically also shifts some stuff, I suppose. Oh fuck, you can't really do that. All right, so there's also bit mask immediate. It's probably not that. Okay. So register. So let's do register. Copies the value in the source to the destination register. So and what do we have in here? Yeah, so this is destination register. Equivalent to, or I don't know what it is. Wide immediate. General purpose register source destination. General purpose encoded. It's a wrong one. So wide immediate moves 16-bit immediate value to the register. This is an alias to move Z. This means the encoding. Okay, whatever. And immediate for, well, yeah, immediate 16. This is a register. Well, this one is immediate to register. So this is the one that we want to use in here. What is this value? Because this is not the value that we're trying to do in here, actually. Right, so what's that? Wait. If I do lang. Two to the 17. Oh my god! Freaking C. No, it's fine, isn't it? Wait. When I do -1, fuck. Yeah, order of operation, yeah. So it's order of freaking operations, but yeah. Okay, so the way we have to do that, right, if I understand correctly, is just this. All right, so but that doesn't explain shit, honestly. Right, that explains shit. And let's open hello.s. All right, so that's kind of understandable. Wait, 2 to the power of 16 is just that. But when I do this thing, it's 1. Oh my god. Yeah, I'm sorry. I completely forgot that it's 1. Yeah, so I'm confused. Like, I'm a little bit sick right now, so I'm sorry, chat. I'm a little bit sick right now. So this is... Okay. So that's fine, chat, that is fine. Right, so that's what I wanted. That's what I originally wanted. So everyone calm down. Everyone calm down. I know computer science. I have a degree in computer science. Everyone shut the fuck up. Everyone shut the fuck up. I have a degree in computer science. Okay, so that seems to be working. Okay. So, and that's pretty cool. But then if I don't do that, it's still going to work. So where is the moment when it starts to like overflow and try some other things? Right, so at which point it starts to overflow? That's the real question. And it doesn't overflow, so it can actually store more in there. Absolute coping, yeah, I know. So what's up with that? So what's up with all of that stuff? Like, why 16-bit immediate value? It's significant bits, I think. I don't know. Like, why does it work? At which point it stops working? So that's the question. Like, I don't really know. So hello, let's see. Because at which point I have to start constructing all of that stuff out of like pieces and stuff. So if I put like 17 in here, is it going to overflow? All right. So maybe hello.s. No, it doesn't overflow. So it's 17 at 20, but it's not a 16-bit. Right, so where 20 came from, we were talking about 16 bits. Right, so weren't we? We were talking about 16, where 20 came from. That's really bizarre to me. So there's a discrepancy between like what I see, what the chat says, what the commutation says, and so on and so forth. Alright, so if we try to do that one more time, alright, so an open hello.s still doesn't overflow. Let's try 20, as the chat said. Alright, so this is going to be 20, and maybe that will make it overflow. This is not hello.s. Still doesn't overflow. Alright. So f. Yeah, so, well, I mean, no, we're already over that. So this value... This is a motherfucking million. This motherfucker just moved a million in there. So... Anyways. Okay, so what if I put like this and then just add 1? So it's something about powers of 2, right? So the hypothesis is that it's something about the powers of 2. Apparently it is something about powers of 2. Check the disassembly. What do you think I'm doing right now? The person in the chat saying this. What do you think we've been doing for 2 hours? What do you think we're doing? Anyways, so I suppose it has something to do with powers of 2, right? Something to do with powers of 2, so which is kind of weird. Okay, can I just move million? Okay, can I just move million and just don't worry about this kind of shit? You know what? You know what? You know what? You know what? Let's just give it a try. So what if I go to B? So, and put million. And just something like that. So this is going to be 69. This is going to be A. Let's not do C. Right, let's try to compile this specific program. Right, so foo.s. Yeah, so we're just like moving million. And let's see if it's going to compile or not. Right. So that's basically it. So this is not what I wanted. Bonding, James bonding, and let's take a look at this thing. Yep, so here is 1 million, and let's try to build this entire thing. Okay, so immediate cannot be moved by a single instruction. So it does in fact have something to do with powers of 2. Right, so if it's a power of 2, you can kind of do that. If it's not, you cannot. All right, so we can try to split that into 16 bits and stuff. Interestingly, like we can actually ignore the power of 2 situation and just always do this splitting with move k and everything. So it's all move z. So yeah, I suppose I have to learn about move z then. So move with 0 moves and optionally shift it. Fuck. All right. And so you oh my god. So I think I understand. So internally, if it's a power of 2, it uses move z to sort of like shift that. Bro, how people use ARM and not fucking go completely insane? Doesn't have to be power. Well, yeah, that's true. This is worse than x86-64. I thought x86-64 is ass. This is worse. What the fuck? x86, that's similar, but it's more intuitive, but maybe, like, I don't know, I kind of get used to that. So, yeah, that's fucking insanity, my friend. That is fucking insanity. The sacrifices you have to make to have a fixed size instruction set, exactly. RISC-V has a similar situation. I see. You can just move through. You can just move 1 million into the register. Can you though? I actually kind of doubt that. Right. So because it has like a kind of a nasty property. So with this shift, that's what you mean. Right. We can try to. Right, so how many of these things we have in here? Oh, блядь. Oh, look at that. We can, блядь, take this value and shift it by fucking 6. Brovskis. So why the compiler didn't fucking do that for me? That would have been cool. So just do. I don't know. But I mean, like, I need a general solution. So I need this kind of shit. Compiler is beginning to understand the junk. Yeah, well, I mean, it's like, yeah. I suppose the general solution, the general solution is going to be, I'm going to look at the immediate value, right? Is it less or equal to the 2 to the power of 16? If it is, I just kind of always split it into 2 parts with move and move k. Yeah. So I think that's a good idea. Right, just like always do that. That's the simplest general solution that like I can see. But here is an interesting thing. This is good for values that are 32 bits. These kind of bits, right? So what if I need 64? Does that mean I have to do several move k's and assemble the number out of 16-bit chunk? Holy fuck! Oh my god! God, please help me. I think I'm starting to understand. Unsolved ISA problem. I think I'm starting to comprehend what the fuck is going on, right? So, but you can optimize. Yeah, you can always optimize this kind of stuff. But we're not doing optimization. So I'm trying to come up with a general solution that is just works, but it's not optimal. This is why B uses int16. This is such a funny statement to be fair. I'm pretty sure when B was conceived, ARM didn't exist. Bro, it was running on PDP. So it was running on PDP. So yeah, we have to do 4 moves in Scheiße. Moves in Scheiße. Damn. Okay, so yeah, and it all makes sense, right? So we're just like assembling this entire thing. Let's fucking go. We can, by the way, I just got an idea. I think we can simply always generate 4 instructions no matter what. Well, it's kind of dumb, but I mean, it's easy to implement, I think. So here is the auto var, and so this is the literal. So we have to do this shit everywhere we do arg literal now, right? So we have to do that everywhere we do arg literal. I wonder if I can factor out all of that stuff to a separate function of some sort. Unsafe fn. So essentially load literal guess a arch 64-bit, not necessarily Linux, right? Not necessarily Linux, just like that. Load literal. Let's put literal to register guess a arch. So here we have to specify the output because this is where we're generating the assembly. So string builder, this is where we collecting the text. So the register name, we need some sort of a register name. Yeah, so the literal itself, literal, and it's going to be, what is it actually? So enum arg i64. So this is i64, look at that. Does it really have to be i64? I'm not quite sure. But anyway, so this is where we're going to be doing all of that stuff. So yeah, so this is the register into which we're loading. So load literal to register. So this is the output. The register is essentially x0 and value. Right. So this is what we're going to be doing from now on. So let me grab that. So literal, got that, but this one is 1. So grab that. Literal, this is another one, but this one it's x0. So literal. All right. So and this time we actually have a register. Literal. Okay, so we're done with all of that stuff. So we're kind of factoring out loading literal into the register for guess a arch64. So yes. So for now, I think we're not gonna, support negative numbers less than 0. Right. So to do loading negative numbers is not supported for now yet. Something like that. It's not supported yet. So then we just need to start splitting this entire thing into little chunks. How many little chunks we're gonna have? How many little chunks? So I have an idea. So we can actually have little chunks somewhere here. So here's the little chunk. And this is basically like 16-bit chunks. So we're gonna have 4 of them. And we also want to have something like, all of that is mutable, obviously, right? So all of that is mutable, chunks, len, 0, right? And in here, right, while literal is greater than 0, we're gonna be just like, you know, essentially splitting all of that stuff. So yesu. So chunks len, right? And we're saving literal. We need to do, what is it? And x f f f f, something like that, right? So we're just like doing that. Just doing that, and then we increment chunks by 1, right? So we have another chunk in here, and we need to now shift that letter. Can I just use the monad operation, right? So shift to the right. So we do it like a, oh, it's a Shrek operator. It's a shift right. Shift right equal, right? So it's a Shrek operator. It's not a monadic bind, it's a Shrek operator. Finally, I have an opportunity to use Shrek operator. Thank you so much. 16. So this is basically what we have in here. Monadic bind, monadic Shrek. And now we have to go in an opposite direction, if I understand correctly, right? As we just like load things. So we have to go in an opposite direction. So, and I suppose you can have a situation, Brovskis, when amount of chunks is equal to 0. And that happens when the literal is, in fact, equal to 0. So, and this is something that we have to take into account. Might as well, actually, maybe put it somewhere here, because it's actually a very easy case, I think. It's a very easy case. So literal equal to 0. What if it's equal to 0? SB append output move reg just 0. So, and then new line, and here is a reg, and everyone is happy, and obviously we have to make it a C, and so on and so forth. So what's interesting is that after that, we are 100% sure that chunks len is not equal to 0. So it has at least something. It has at least something. So now what we do, we subtract chunk len, and now at chunks len, we have the value that we want to move into the register. So I'm going to move the stuff in here, right? So here it is. We're moving this specific value. Let's say it's going to be LD, right? So we're going to do, maybe it's just going to be D, just a D value. All right. This is what we got. Might as well actually do something like maybe U. I'm not sure. Let's do D. Let's do D. Okay. So now, while chunks len is greater than 0, we keep repeating this entire process. But this time with move K and LSL 16. Absolute sharding? What do you guys think? Is that an absolute sharding? Look at this shit. This is a very fucking smart algorithm. This algorithm is so fucking smart, I think I can claim this is AI. I think I can now claim that I'm using AI in the compiler. And AI in the compiler is a large language model. Well, I mean, it's a pretty good idea, right? So it's just basically, yeah, so you split it into chunks. Yeah. So AI is now AI. All right, so is it gonna work? Is it gonna work now, yo? Litera. Fuck you. What else? Aha. Brovsky, can you just like as U16? Can I just do something like let literal as U64? So I think I should be able to. So honestly, the way you can shadow variables in Rust is kind of convenient sometimes. So 13 on 2 hours of sleep is a masterpiece. You mean stream, right? So, but I mean, that's understandable. So I suppose what we have to do as U16. What else do we have in here? Okay, chunks. What the fuck do you want from me, Brovsky? So chunks cannot pass U16 to variadic function. Huh. Well, pass it as 64. Mute chunks. Variable. Wait a second. I'm writing into this variable and you're telling me that this variable doesn't need to be mutable? Cannot assign twice to immutable variable. Well, I mean, make it mutable. Alright. Chunks isn't initialized. 0 yet. Cannot assign. Fuck you! Like, you motherfucker told me to remove the mutable and... like, I mean, on top of being anal, this shit has schizophrenia. Like... like, I wouldn't mind if it was just anal. On top of being anal, this motherfucker is also dumb. Like, holy fuck. Anyway. So, I don't mind anal. Don't fucking clip that out of context. So, what do we have in here? So this is like a result. It also complains about unused results. Ah. Right, so let's actually put this kind of thing. Alright. So, yep. So let me take a look at the example we have in here. So this is 1 million. This is 1 million. If I now open l'assembler, is that the same as we had there? It's actually kind of different, to be fair. But I mean, it does split things. We can actually test different things, right? So if I put 3 in here, and just like now, try to open this stuff, revert. 3 is totally fine. Okay, so 1 million. So let's see if it's going to work. Right, so 15. 15. Where is my Python? Where is my Python? So 15, in terms of bin, right, it's that. Okay. So, and I suppose then I move it by 16, and then I add this value. Oh, fuck, this is not what I want. I suppose what I have to do here is that, and if I look at that value, oh, I'm just building it differently. I'm just building it differently, but I mean, you end up with basically the same, don't you? I think you end up with basically the same. So, all right, so let's give it a try. I'm gonna recompile one more time. So where is SCP? Yeah, I have to go to, yeah, already in a correct place. Bonding. Oh, cut foo.s. Okay, so here's all of that stuff. Let's rebuild. It compiled. Fuck you! What's wrong in here? So, am I doing... I think I'm doing something very stupid. Yeah. So we actually move values are backwards. Are they? Are they backwards? So if I... Okay, let me try. Foo.s, so are they... Yeah, I think they're backwards. How did I end up with backwards chats? Can anybody explain to me? Huh, that's bizarre. Yeah, it's backwards. What the fuck? Am I getting tired? Load literal. So that means that I have to actually process them from the very beginning, right? So from like 0 and stuff. Damn, okay. So I didn't expect that, but that's fine. So it's 0, right? And I just process this thing like that. So it's I. I plus 1. I plus 1. So in here, I is less than chunks len. So in here we just do chunks I plus 1. So that's what we're doing in here. So that's what we have to be doing, I think. Alright. So foo.s. So it's now the other way around. Cool. It's kind of interesting that I basically reproduce the same situation by analyzing assembly. So somebody asked in the chat, I think on a break or something, like maybe not on a break, how do you learn assembly? And I said, just look at what the compiler generates and learn from that. Here's the demonstration. Right, so I don't know how to store big values in a particular place. I just generated, pondered upon it for quite some time, and then understood it and just used it. So I literally demonstrated how you learn assembly, because I myself don't know assembly. All right, so I specifically ARM assembly. And x86-64 I also don't know it, right? So I just know some small subset. I just know a small subset, and it's just like if I need to learn more, I just like learn on the fly. So that's how you do that, right? And I don't think there is a one single book that teaches you the entirety of assembly, except maybe Intel manual, and also maybe there's an ARM manual. But yeah, that's how we do that. That's how everybody's doing that, right? So there's no a single centralized place where all of that knowledge is kind of stored. And your job as a programmer is to like mine that knowledge out of different places, right? So essentially, chat helps a lot as well. So thank you everyone in the chat. So we're kind of together discovering all of that. So. So this is not really a pair programming, it's sort of like a group programming, like a group masturbation, but it's a group. Who needs pair programming if you can have an entire group programming, right? So anyway, so let's actually upload this kind of thing to the virtual machine and let's build the entire thing. So let's actually take a look at for S. All right, so I can build this entire thing, and then in 4, it is 1 million. So I can actually go a little bit more interesting. So let's open foo.b and 1, 2, 3, 4, 5, 6, yeah, 7. This is like more than 1 million, right? So, and it's a pretty good testimony to this approach. I think it is. Right, let's do that. Foo.s. And this is our splittage. So this is how we split things around. Pretty cool. Let's upload that. Bonding, James bonding. Let's rebuild the whole thing. Foo and absolute trading. Absolute fucking trading. I mastered constructing literals in the registers. It's not that hard actually, right? So once you wrap your head around it, yeah, it kind of makes sense, right? So you have to assemble it. You have to assemble it. Mob programming, yeah, that's a good term. It's not pair programming, but mob programming. So, all right, so we managed to do that. Now we understand this kind of thing. So let's go back in here and let's open hello SC. So let's actually start with a small value, right? A small value is something like 3. Right, and let's compare it to 4. And I do that intentionally so it doesn't start splitting literals and stuff like that, so it doesn't become very noisy, right? So we want to keep the assembler less noisy. Right, let's do terminal, make -b. Okay, let's open hello.s. What do we have? Damn. Okay. CMP, I already see familiar shit. CMP. And it probably sets the flag ls. That is actually very fucking straightforward. Bro, I didn't expect that it's gonna be this straightforward. What the fuck? That's actually almost like x86-64. Like, what the fuck? Alright, so I want to take a look at cset. What is cset? Conditional set. Sets the destination register to 1 if the condition is true, right? And the condition is what? So invcond, okay, invcond is one of the standard condition including AL and V encoded with the least significant bit, LT equivalent code to cond GE. So, and we looking for LS. I suppose it's just less, right? So I don't really know what the fuck they're trying to say in here. Equivalent to cond high. So ls equivalent to cond high. High is equivalent to cond ls. Thank you. So they literally recursion in my documentation. What the fuck? Yeah, so ls, I don't know, lt equivalent to greater than. LT is actually equivalent to greater than. I suppose we have to do ls. Anyways. Let's go ahead and try to do some scheiße. So this is going to be A. We're going to put 34, and then we're going to also allocate C. And then C is going to be less than 1 million, right? And then I want to actually output this thing. Okay, so let's actually start compiling. Okay, it's panics in here, which is understandable. Left-hand side and right-hand side are x0, so that means we should be able to do x0 in here, hopefully. So this is going to be something like SB append. So CMP x0, x1. So it probably doesn't need to be comma in here. So we'll get some subs, by the way. I haven't acknowledged subs in a while. I'm really sorry about that. I was really consumed by the programming. So Danny Heck, thank you so much for the subs. Hi, what did I miss? Greater than... Oh, PS. This thing banned me from introvert party. So ping me in Discord. Ping me in Discord and tell me to give you VIP. Right, so... once you have VIP, you don't need sub to actually be in a Discord. So, why software? Thank you so much for Tivan with the message. I love this project. Cheers. I love it too. It's actually really fun. I'm having a lot of fun right now, with, like exploring this assembler. And I'm actually not only exploring it, I'm learning how it is more efficient to learn about the instructions, so I can continue implementing the rest of the operations. Right. So I'm sort of meta learning, if that makes any sense. Anyways, so SB append, and what we need to do in here is, yeah, we're setting. So C set 0. So can I can actually set this kind of stuff. So it's set destination to 1, otherwise to true. This is a rather convenient. Output S1 like this. C set X1. So when the condition is ls, right? So we set it like that. Hopefully that will work. And then now we need to save this value back. Right, so we need to save this value back, and this is how we're storing it, right? So we can duplicate this thing, but I feel like any binop is going to end with this operation anyway, so we need to put it at the end in here for everyone, right? So we can assume that left-hand side and right-hand side are in x0 and x1 correspondingly, and after you apply the binop, the result of the binop is going to be in x0, right? So we should then save into the corresponding like result index in here, right? That makes sense. Okay, so that's pretty cool. Alrighty, so now if I take a look at the foo.s, that's a lot of code actually, damn. Okay, so here is the CMP, and we do cset, and then we save in that result into the temporary variable that we have in here. Right, and this variable, we then loading back. So we do a lot of weird assignments at some point, but we need to do that to then call. Oh yeah, so we're assigning it into 24, right? So because the compiler is not optimizing one. And then we use this 24 as one of the argument in printf, which is exactly what we have in here, right? So that makes sense. That makes a lot of sense. Okay, compiling one more time. Let's do SCP bonding. Okay, so let's go to a different tab. So this is foo. So the resulting assembly is actually slowly growing, right? So it becomes kind of difficult to read. So it looks like a legit compiler output now. So, which is kind of cool, right? So the complexity is growing. We started with a very simple program, and now we're making more complicated stuff. Right, so let's try to rebuild. Okay, and it prints 1, which is exactly true. So we might as well now maybe put something 1 million like this, 1 million and 1. All right, so let's try to compile this entire thing. And I want to take a look at the assembler, right? So because, yeah, so it does this move k thingy twice already. Look at that. So here is the pattern. Here's the pattern that we implemented, and it's reused throughout the code generation. It's reused throughout the code generation. So we need to implement it only once, and now every time it encounters this opcode, I mean intermediate representation instruction, it just like reuses it all the time. Yeah, so pretty cool. So SCP bonding. Right, so let's rebuild this entire thing, and I'm gonna run it, and it's 0 because it's false. Perfect. So that means in the Fibonacci example, in this one, this part is implemented. This part is already implemented. So the only thing that is left to implement is while loop, because the rest of the stuff we already have. Only loops are left. Exactly, only loops are left. Let's fucking go. So I'm gonna try to directly compile the Fibonacci example. So where is going to fail? So that is unexpected. Because I forgot to exit when it's 0, which is understandable. So that's totally fine. All right. Jump if not. There you go. Jump if not. So what do we have in here? Jump if not. So these are the things that we have. And depending on this kind of argument, so this is the value, right? This is the value. And we need to check whether this value is equal to 0 or not equal to 0 or something. We'll see how it goes. We'll see how it goes. Okay. So let's open Hello C. So we want to probably start with something like this. While a is less than 5, let's say, we're going to be doing something like printf lu a, and then a plus 1. Very simple program. Let's actually see how the compiler does this entire stuff. foo.s. This is not, so it's a hello.s. Okay, so we got some stuff. All right. So, oof. So str xzr. Ooh. So this is where we call. This is where we call printf, and this is where we do like increment by 1, right? So that makes sense. That makes a lot of sense. So we also have lc0. So this lc0 thing, it makes me think that I fucked up something. Right, like where is a? I remember actually putting a somewhere there, but it's just like not there. Because x1. Okay, so here is. Okay, so it put second argument in here. So it first put the second argument, and only then it constructed the first argument. Okay, so that explains it. I'm not sure why I did it like that. So it would be better to actually do it like this, but whatever. So then B2L. So this is a conditional jump. I know it when I see it. So B is probably branching, right? B is probably branching. So there's str, x, zr, or whatever. Then at the end in here, it put a condition. Okay, this is unconditional jumping, I suppose. That is complicated, honestly. That is complicated. All right, so I think this is yeah, B is unconditional. I already can see that. But what is str? I see. It unconditionally jumps to the place where it performs the comparison, and then conditionally jumps. Okay, so it's just like it organized a loop not the way I usually organize it. That's kind of interesting because I usually keep the condition at the top, right? Just like in a while loop. They put the condition at the bottom, right? So this thing just unconditionally jumps to the bottom where the condition is checked, where it just loads the value, right? It just loads the value, performs the comparison, and does BLS. Aha. So that's kind of similar to how x86-64 works, right? So you do the comparison, it sets the bits, and then depending on which bits are set, it will jump there. So in our case, we already have a value stored in one of the variables. We just need to check whether it's 0 or not. We can do a comparison and then maybe BZ. Is there something like BZ thingy? Or maybe B equal. Yeah, well, we can do that. B and Z, yeah. Let's actually see, B and Z. So it's a conditional, you see it's a conditional thing. So B back. So there's a BLS, okay. So probably have to, where our branch? Aha, I see you, motherfucker. I see you, And what do we have in here? So NV, I don't know what the fuck is that, but there is an equal. All right, so we can do back. So what do we want to do? We want to load the arg. What's interesting is that we have a lot of repetition with loading the arg. We might as well actually factor it out into something else, but I'm not going to be doing it right now. Don't feel like doing it right now, honestly. All right, so here is the arg. I'm loading the arg into x0, whether it's like a value or not. It's like I know that the condition is in x0. So, and now I'm jumping. How do I do this thing? Jump if not in x86-64. In x86-64, I just check. So I'm jumping if it is 0. All right, I'm jumping if it is 0. So that means here I can do append output. So can I just do? Yeah, I can compare with numbers. That's fine. CMP x0 0. Okay, so we're comparing it to 0. That's understandable. And then we do back, and we're jumping to the OP ZU, which is the address. So this is a conditional jump. This is conditional jump. We may right away implement unconditional jump, which is not that difficult to implement because it's just jump to the address. So this is ADDR, and we can just put it like that. And it's going to be basically B. Damn. I think ARM is kind of perfect for our programming language because ARM literally has a B instruction. The B instruction because it's a branch. Branch, not brunch. Branch. B. B. So, oh yeah, we have to actually do something like this. So let's remove. Fuck you. All right, so that seems to be working. Now, if I take a look at the example fib.s, look at that. This is the final Fibonacci example, which is not that big, honestly. Right, okay, so do we have BQ? Okay, so it jumps to OP10, and inside it jumps over unconditional jump that jumps back in here. And inside of this entire thing, we do a lot of, yeah, so this is just like shuffling around different temporary variables and stuff like that. And here is the printing. This looks kind of better than x86-64, right? So where is the assembly? Yeah, so here's the, yeah, this is x86-64 and this is ARM. Yeah, kind of interesting, ARM is actually superior. I think they both are shit. Honestly. So from my experience, like in these two streams, let's not talk about it. Anyways, so let's actually now copy example fib.s. I'm copying Fibonacci there. Bonding, James bonding. All right, so are we where? Okay, so let me take a look. Here is the fibs.s, and I can do less fibs.s. Okay, that's pretty cool. So I want to actually open makefile. So what do you want? Okay. You know what? I'm gonna copy paste you. And in here, I'm gonna just do foo fib g. Who needs wildcards if you can just copy paste code? Who need templates? Templates are only for people who don't know how to copy paste because of a literal skill issue. I'm telling you. All right, so let's rebuild this entire thing. Make that be, and that compiles. Chat. Fuck. Chat, calm down. I think I'm the one who needs to calm down. Right, I want to just like reassign the chat like this. And everything compiles, right? So everything compiles. Absolute choosing. 2 fucking days. 2 fucking days porting this goddamn freaking Fibonacci example to ARM without knowing any freaking ARM, and we did it. So it's not like fully supports ARM to the extent it supports x86-64, but it works, right? So this specific example works and generates Fibonacci numbers on ARM. Holy fuck. That's so freaking cool. That is absolute charging moment. Honestly, that is absolute charging moment, right? So props to everyone who's been here live, right? So because you just witnessed the legendary freaking moment. I'm currently sick. I have a cold. I can feel that I have a elevated body temperature, but I still grinded through and delivered the port of this goddamn Fibonacci example to ARM. How about that? So let's fucking commit that. How about that? Let's freaking commit that. So we're not going to be committing maybe array lib.b. So we have a lot of stuff in here that needs to be maybe git ignored. So I want to git ignore specifically also s and maybe ir. We don't need any of that stuff. So none of that is needed. And actually, yeah, none of that is needed either. Asking too many questions. So this is how much code we wrote in a span of 2 days, right? So this is how much code we wrote. Okay, so now introduce gas arch Linux target and port fib examples fib.b b to it, and I'm gonna push that right into the repo. So it is live in a repo. You can play with it if you're interested, right? So now we have ARM target, right? So it only generates assembly, so it doesn't properly link or anything, but I'm gonna fix that and finish it already later, right? So we finished the scope of today's session, right? As I already said, the scope of today's session was to actually port the Fibonacci example to ARM, right? No more, no less. We actually achieved that scope, and because of that, I think it's fair to say that the session is successful. So we'll get some subs. Right, so no, we don't have some subs. Right. I guess that's it for today. Thanks everyone who's watching me right now. I really appreciate that. Have a good one, and I see you all on the next recreation programming session with Mr. Zozin, where we're gonna actually port this language to more different platforms. All right, so we're definitely gonna check RISC. We're definitely gonna port to WASM. I'm also thinking somebody actually suggested in YouTube comments to port it to UXN, right? So that virtual machine, small virtual machine, I think it's gonna be perfect for that. Right, so a lot of cool stuff waits us ahead. Thanks everyone for watching. Love you all. Mwah.